Hey, and we're live. We did it. We're here. We are in the Discord with the lovely Local and Eternal, and we're live. They appear to be both be muted, but we'll be there. They'll be here for when it's important. Hey, Local's here.
Yeah. You were both deafened, so I was like, I'll mute in case he's got some big spiel when he come back. I don't know.
Nah. We're just getting right into it. We
Yo,
are going for it. We're gonna actually write some code today.
you can't hear it, but I clapped.
What's up, Lucy or Lucky? 2010. We got Isinin. And I don't know how to say that. I'm going to go with Miranda. How's it going, Miranda? Hey, Lenzer. Hey, chat. How's it going, Miranda? Let me see what I can do here. Okay. We are good. I'm finally dipping in the pool of Linux from scratch. What is Linux from scratch? Oh no. It's only a few million lines. It might take you a little bit. Oh yeah, so it seems that we've had lovely progress on the rewrite and by Local here. As well as I have so much stuff open. Jesus. I won't close. We'll get there. I also never checked if I was streaming. I really got to get better at that because one of these days it's going to bite me for sure. How's everybody doing? Welcome to the stream. Thank you for tuning in. Too much stuff open. Oh, it's got a pop-up. That's why. Fantastic. Okay. And we're going to go to the intercept rewrite today. I don't think we're going to be building very much, but we'll see how it goes.
It should build, though.
It should build now?
It's been building for me for all day, basically.
Nice, okay. Something I didn't talk about, local celebrity, if you know what I'm saying. Miranda said, you basically compile everything from the sources and sort of make your own Linux distro. Nice, that's not too bad.
That's what I figured it was. I didn't want to jump in.
So I did do something. If you were using TDM GCC like I was before, I'm sadly no longer using it. I would be using it, but it's too old, and I don't have the time to figure out how to update it right now. So that is that. Anywho, I switched to MSys2 MinGW64, and I put that into my path. And now when I run GCC, it is actually built by the MSys2 project, and it is 13.2 instead of 10.3, so I have a much more recent GCC, which is fantastic. Hopefully, this means that I won't have to use Clang to build this thing.
What the hell?
You okay?
Nah, hopefully this means I won't have to use Clang. What does that mean?
I like GCC and the stuff behind it.
I
Free
know.
software. Free as in freedom, baby. So I'm going to configure a new CMake build tree using the Ninja build system, and that should use GCC by default. See, before I was having to use Clang and do all this nonsense. We probably do need the intercept test linker to be Clang because of... We don't technically need it to be Clang, but it's easier to use Clang because of reasons. Basically, Eternal wrote it and he uses Clang. So that's why. What is the license of Clang, asks King Buns. That's a good one to ask. I'm pretty sure I know off the top of my head, but I don't want to be wrong, so I'm going to look it up for you. Off the top of my head, I would assume that it's Apache v2, but I can't remember. Yeah, it's the Apache v2. I remembered correctly.
Woo.
So LLVM at least 14 is, or maybe that's the version of the, yeah. At least LLVM 14 is released under Apache v2, which is compatible with the GNU GPL V3 question mark? I think it's the V3 or the LGPL V3. I can't remember. It's one of those. But basically it's very similar. It's near free software and it's accepted by the OSI. So we like Clang. It's open source. It's fantastic. We can build it ourselves. However, I can't build it myself, so that's why I'm kind of biased against it. And also, it's an Apple thing. It's not an Apple thing, but it's an Apple thing. I don't know why. It's just in my head. It did build. Holy crap. There's tons of warnings, but that's not too bad. That's how it was before.
That's why I made that freaky W card change. I just wanted it to build.
Hey, I see. And you want to hear touch xlib? No, we're all still alive.
Oh.
Xlib's old. Xlib,
hello.
it's not that bad though. Hello, who is it? It's Melody.
Melody.
I can never say it
Thanks
right.
for
Thank you.
remembering the pronunciation.
I'm trying to make a program that uses xlib. Well, hopefully you know about local sockets and how those work.
We're popping off. Maddie here.
Okay, so we're going to start writing part of the library for Intercept, which is going to be probably codegen.cc is what it'd be called. Does that feel right?
You mean the code gen for LCC?
No. We're going to be doing the IR generation code gen.
Yeah.
Of
Which is in
Intercept.
LCC.
That's for Intercept. That's the front end.
What? The IR is in the middle. It's in LCC.
Yeah, we're gonna include the IR from here.
Okay, so you're doing the IR gen, not the code gen, like backend. Okay.
Maybe. I'm pretty sure. Yeah, we have to pass an IR to LCC, don't we?
Yeah. No, because the word code gen to me just meant like take the IR and code gen it. I was like, I don't know you're going to do that yet, but
yeah. So maybe this is a good time to look at it too. In the compilation overview document, I can't remember if I've done this yet, but I had this plan. I haven't done this yet. Basically, in the front end itself, code gen refers to the IR because that's the only code gen that's done in the front end. So we generally call like IR generation the code gen because you take the AST and generate IR code from it. But then like there's lots of code gen that happens in between there where like there's the general MIR and lowering into that, and there's lots of things that go on. This is just what it was called before. Should I just call it irgeneration.cc? Or irgen? Underscore? I think with an underscore. irgen. Otherwise, people are going to be like, what is ergen? We're going to go with irgen. Anyways, we're not going to make much progress here. Because
CodeGen doesn't have an underscore. So
what was that?
CodeGen doesn't have an underscore in it.
It doesn't.
For the file name. Wait, what? Okay,
yeah.
Never mind, sorry. Okay, never mind.
So CodeGen, I just call that one word because I see it as one word when I like look up things. But IRGen isn't something I see all the time, so I want to make sure it's very distinguished that it's IRGen and not like IRGEN, or you know what I mean? Because at some point, someone's going to look at this and go, what the hell does this mean?
Mm-hmm.
And that will probably be me. Anyways, we now have all the headers in an include directory. Big sad. And we have the IR, which has apparently, it's very much written. So we have an IR value, which is basically an instruction, is how we can think of it, but also blocks and functions are these things. So don't worry too hard about it. But basically it's the same IR instruction we had before, just written into a little more concise form so there's less code duplication between things. Fantastic. And then we have, yeah, here's an actual IR instruction. You see value is, instruction inherits from value. Fantastic. And it has a machine instruction that we're going to generate from it. And yeah. See, in this case, we use CodeGen in the sense of like the backend because we're in the IR file right now. So CodeGen, in this case, early CodeGen refers to like when we're lowering the IR and stuff like that. And into general MIR. It's funky. But it's also the easiest way to talk about things. I think IRGen will help a lot. We have this plus, the unary plus being used to get the underlying value of an enum. C++ is so funky. Okay. So yeah, we have basically everything we need, it looks like. Do we have a type? Does an instruction have a type? I don't see type here, which is a little worrying. Oh, I do. It's here. Does it go unused? It goes unused. Is that true? Value gets initialized with... Okay, does value have a type? There is... Okay, every value has a type. Fantastic. Why are we not passing? That's got to be a bug, right, local? We're supposed to pass...
I can't see what you're looking at. I'm not on your stream and you're not sharing in Discord.
I'm not sharing in Discord?
Nope.
Oh, I'm an idiot. What have I done? Okay, here we go. Live times 2.
Double live. Okay, what are we looking at? I wasn't paying attention.
Okay, so this instruction, IR instruction, inherits from value. And it initializes it in its constructor, right?
Yeah.
But shouldn't... T is unused. Shouldn't we be passing T here? Because if we go up to the value constructor and take a look at it, it's type T.
Yeah, I would do that.
Okay.
I didn't write that, but that looks right.
Why?
When Eternal gets back, he can tell us the semantics of passing a type to a constructor and why it's wrong, but I think it's right.
Yeah, I like that. Okay. So when we create an IR instruction, it must have a type. And this is assumedly a type check type, so we know it's correct. We haven't done type checking yet. Don't worry about that. We're just assuming everything is correct. So, yeah. That's the type dealt with. So every instruction has a type. We're going to need that for some sort of information. Lots of information, actually. And then this is actually going to be an IR type now, an LCC type, not an intercept type or a LAYA type. So intercept is going to have its own idea of what a type is, as we can, I'm sure, see here. This is an intercept type. It's going to be different from the IR type. It's going to need different things and just be a completely different thing, basically. So we're going to have to convert intercept types into IR types, which makes sense.
Yep. It's a baby
Stay
LLVM,
hydrated.
basically.
It's a baby what?
Baby LLVM.
Yeah. It is. It's our little baby LLVM. And it's going to be hopefully never as big as LLVM, but as far as like code size, we don't need to do everything. This is going to be a good little way to get new languages up and running. Where are we at? Where are we at? So we only have function types in the IR. That's kind of a problem. We need more than function types, right? Do you think it makes sense to have an integer type in the IR? It must, right?
Yeah. Maybe only one integer type with a width, but yeah, you need at least an integer type.
Let's do that then. Oop. Okay. If anyone has questions, by the way, ask them. Eternal should be back in, I don't know, 5-10 minutes or whenever he's back, and we can ask him things like,
It's
do
a
we need
little
an integer
unwieldy,
type?
Lance, but do you have both chats open or just the Twitch chat?
I've got both.
Okay, good. Just making sure.
I haven't been reading it, but I am now.
Okay.
I did have them open. What is the GitHub page right now that was linked yesterday? It's our baby LLVM. Opaque pointers. What have you done? You've linked
So,
to opaque
PTR.
pointers.
Yeah, just talking about opaque pointers, the LLVM. The PTR keyword instead of having actual pointer types.
I see. Yeah,
In LLVM. That's just what we're talking about.
that's definitely what we're doing for our.
Oh yeah,
our
we're not
IR.
doing typed pointers in the IR.
We did have that, but only because I wrote the IR. When I didn't know what I was doing. And I was
That's one
like,
of the primary reasons why the syntactic types are different, is because the IR types are so much simpler. You can't represent them in the syntax accurately
exactly.
for
And
semantic
then
analysis.
for a pointer, the only time you need to know the underlying type is when you load or store it, right? So then IR instructions that are loads or stores just store the type that they're storing or loading, and then everything's hunky-dory.
Yep.
Okay, so class integer type is a public type. I think we're just going to have one usize. See, do we want to do a member? We probably want to do a member, that way it can't be changed, right? So we're going to do like underscore
At least
with
with an accessor and a mod, like, because we in the IR we really want to worry about the invariance. So everything should be private by default until we know otherwise.
That's what a class is private by default, right?
Yeah, which it is. Yeah. So then you can do public after your usize width to get everything else to be public.
Okay. Fantastic.
Funky formatting.
Is it?
No, that's fine. It looks fine now. It just
Oh, okay.
automatically indented for you.
Yeah. It's I there's so much I have to set up. I haven't written C++ in a long time. Okay. So with this, we're going to need a constructor. Can this why is this constructor private? What does that mean?
Assume it's because it's going to be created through like a constructor function on the IR, like IR add function type or something.
Oh, so it's a friend.
Again, I didn't write the IR, and
Okay.
Eternal just got back, so you can ask him now.
Hey.
What?
See if I'm right.
So the IR, why is the constructor private of the type, of the IR type?
If you look at line 53, it's a friend of context, so that's why I made that assumption.
The reason why it's private is because IR types are going to be cached, so you're not supposed to ever create a new one. You're just supposed to call this get function on line 73. That should actually be static. I don't know why it isn't. It should be.
Like that?
Which will look up the type in the context and return it if it already exists. If not, we'll create a new one, put it in the context. So we don't create 10,000 void pointer types or something like that.
So the get
In
should
the
be
IR, that makes sense. In the AST, less so.
Yep.
That's why it's the context is private, because is a friend, because it creates the types and stores them. That's why. Anyway,
you don't need the params for your, or the return type for your integer type. You just need the usize.
I know. I realized that after I looked down there. I was like,
typing. Yeah.
It
should also be
get integer type also probably doesn't return a function type pointer. Just saying.
That too.
So this will be an integer type pointer. This will be the width.
Yes, good. Also, one more difference between the IR and the AST. In the AST, you're supposed to create new copies of the built-in types, so you have location information. In the II, you're just supposed to reuse the ones that already exist in type.
Mhm.
Nice.
Don't forget to make it public, Lynn.
Also, why there is no, at least currently, there is no primitive type, because you're just supposed to compare those by pointer, basically.
There we go.
Anyway, are we live already?
Yes.
Okay. Then to minimize problems, I'm going to switch over to Discord in the browser, so this entire thing that happened last time doesn't happen.
Are we gonna need a type?
No, it is the type.
It is the type. Man, this is confusing. Why did he only make the function type? It's the most complicated one.
So
It's so
you
hard to
just need
build
use
off
have
of
width.
it.
That's all you have. It's just the width.
It's just funky, man.
And
And then I have to
And,
initialize it.
We've been implementing small functions in header files, so if you wanted to go ahead and implement width in here as well, just const return width.
Yeah.
yeah. It should be called bit width or byte width, otherwise we will be very confused about which one it actually is, and it should probably be bit width, yeah. Okay, so should we do the thing now?
Yeah, let's do the thing now. I don't know how we're gonna do the thing now, but we're gonna make the thing now happen.
What I'm gonna do is I'm going to share my screen.
That always goes well.
That's why he's in the
Yeah,
browser.
now I've switched to Discord in the browser. It should work. Let's see. Okay. Just need to find the window. Presume it's this. You see the thing? I think you can.
Can I see the thing? I can see the thing. It's very wide.
Okay, is this better?
Ah, that's much better. Fantastic.
It's much
fantastic.
better. Okay, I'll put Discord over here then.
Can I?
Okay. Shall we get started then?
Hold on. I gotta. Uno momento. I gotta figure out how to show Discord real quick. Instead
I'm gonna
of
open the stream chat in case anyone has questions.
good idea. There is
well, I always
questions.
find that down here.
So I think I'm gonna go to Window View,
Okay.
fix the chat. Hello everybody, welcome back. And then I'm gonna put the Window View over to the Discord. Well, that's funky. Hopefully that's a little better. And then I'm gonna full screen
Plus
this.
has at least 2 ways to note the return type. Yep, I'm pretty sure it's just. I mean, this before or after. Yeah, basically.
Does this?
Tactically, there's just 2 ways.
Okay, you're gonna have to remember in the bottom right there's a chat.
And here, I presume.
Yes, a little bit bigger than that,
Okay.
but yeah.
Okay. All right. I'm gonna just keep it up here then. So today we're talking about value categories in modern C++ because let me get closer to the mic. Maybe that would help. Because we're writing this compiler in C++ now, and there was some confusion regarding what moving is and how any of this works, we're going to talk about that today. So, this is basically divided into 3 parts. First we're going to talk about the situation before C++ 11 and how L values and R values were defined back then, and how const references work. It's important to note, though, that this doesn't mean that any of that is outdated. The semantics of all of that still apply, at least the motivations behind that. It's just that the terminology has changed after C++ 11. And then part 2 will focus on C++ 11, moving, X values, and so on. And then part 3 discusses just forwarding. That's going to be the smallest part. So, let me zoom in a bit more. So L values and R values. L values, the term L value is pretty old. I think I'm pretty sure it's from like CPL or BCPL even, like which was which the language came before B, which came before C. And L values originally stood for left-hand side values or locator values. The reason for that is that they are values that may appear on the left-hand side of an assignment, or equivalently, values that occupy a location in memory, hence locator value. And that includes things like static and automatic variables. Automatic variables is the official quote-unquote term for local variables. It's also where the auto keyword comes from originally. Function parameters, because they're just variables. Pointer dereferences, because pointers hold addresses. Subscripts, because they're either pointers or arrays, and arrays are just blobs of memory. Sort of by definition, an expression of reference type is an L value. We'll get to that. And also some other built-in operations also are also L values. For instance, let's consider these declarations here that we're going to be using below. So returns reference just returns an int reference, returns value returns a value, and we have an argument of type int. And then in the body of this f function, we could write things like this. All of these are L values. Static variables, local variables, arguments, references, array accesses, a function that returns a reference, and also perhaps a bit surprising are these two, especially this one, a parenthesized expression. If the inner expression is an L value, this entire thing is an L value. And the same thing goes for ternaries. If both the then and else branch are L values, this entire thing is also an L value. That's sometimes useful. As you can see, we can assign to all of this. If you put this in a compiler, this will in fact compile. Now, what we've just mentioned is that some operation, the ternary example is a bit cursed, as someone is commenting, yes, but it's also an L value. It's not too common that you use this, but it exists. I'm not sure about how this works in C, though. This might be a C++ thing. I'm not sure if a ternary is an L value in C. Now, some operations that we've already mentioned are only supported on L values, and most prominently that's reassignment, as we've already seen here, the address of operator, because you can only take the address of something if that something lives in memory. You can't take the address of for. And then also reference binding, because reference binding is just taking the address. These two are kind of equivalent. As you can see, we can do all of that with a static variable. Now, and conversely, you can't do any of this on things that are not L values. For instance, you can't assign to for. You can't take the address of for, and you also cannot bind a reference to for. And xCatalyst_TT0 in chat is commenting that conditional operators do not count as L values in C. That can very well be the case. They are L values in C++. I wasn't sure anymore about how they worked in C, but I think they aren't L values in C. You might be right about that. But in C++ they are. But this example is just here to show that for built-in operators such as ternaries, whether something is an L value or not depends on the operands. So here's some more comments as to why these are all in memory. We've already discussed that. And here's another illustration of how the ternary thing works. In this case, a static and automatic variable are both L values, meaning the entire expression is an L value. However, here, one side is not an L value, so the entire thing is not an L value, so if you try to compile this, it will fail. Now, we may have already mentioned that, but anything that is not an L value is called an R value, which stands for right-hand side value, because R values cannot appear on the left-hand side of an assignment, because again, we can't assign to for. Because for is not something that lives in memory, it's a constant. You can't change the value of a constant. And for instance, a few examples of R values include things like integer literals and float literals. The results of most built-in operators, for instance, if you have a plus b, the result of that is an R value, not an L value. But this very much depends on the operator, and it can also depend on the operands, as we have seen up here. And finally, calls to functions that do not return a value of reference type, which includes our returns value function up here. And there are a few examples of this here. You can't assign to for, you can also not assign to the sum of two variables, and you can't assign to a function that returns a value. These are not exhaustive descriptions of everything that is an L value and everything that is an R value. If you really want to figure out everything that is an L value and R value, look at the standard. For every built-in operation, it describes what everything is.
But in general, the definition of whether something is an R value and L value is also just listed. It's given by listing all the things that are L values and R values. But instead of memorizing everything, it's better to keep this distinction in mind that the idea of an L value is something that lives in memory, whereas an R value is something that doesn't live in memory typically. Now, any questions about this so far?
So, a local, like if I make an int a within the main function, that's in memory. What part of that is an L value?
What do you mean by what part of it?
Like, is the variable itself an L value, or is each time I use it, it can be an L value? Do you see what I'm saying?
Interesting question. We'll come back to that a bit later. Let's put it that way.
Okay.
At the end of this.
Fantastic.
But that's a good question. Any other questions?
I don't see any.
Okay. So let's do a small interlude on const variables. What about const variables? If variables are L values, what are const variables? Because we've just established that you can reassign L values, but you can't reassign const variables, obviously. So what are they then? Are const variables R values? Well, no, because you can still take the address of a const variable or bind a reference to them. So what are they? Well, they are considered L values because they live in memory, but they are not modifiable, and that's why they are called non-modifiable L values. So L values all live in memory. You can always take their address or bind a reference to them, but not all L values can be modified. There are some L values, such as const variables, that are non-modifiable and that do not support reassignment, but that otherwise behave just like L values. Now, as a side note, if you want to bind a reference to, for instance, a constant int, the resulting reference type is a const int reference. That has nothing to do with R values or L values. That's just the type system. If you want to bind a reference to T, you get a T reference. And if T happens to be const, the reference also has to be const. So this is an error if we try to bind a non-const reference to this const variable, but this has nothing to do with L values or R values. That's just a different part of the type system. Okay, a few more notes about these. Unlike number literals, which are R values, string literals are considered L values, but since they're of a const type, they are non-modifiable L values. The thing about string literals is, though, the fact that they're L values rarely ever matters. Like, you can't really do much with them that you do with L values typically. It's mostly a technicality because the standard specifies that they live in memory and that they are L values because of that. So the fact that string literals are L values, there's no real rhyme or reason as to why that really has to be the case. You could just as well find that string literals are just like number literals, but they just happen to be arrays. That standard could have done that, but it didn't. It's probably because that goes back to C, and there may have been some reason for that originally. And someone's asking, is the int reference also in C? No, only C++ has references. C does not.
Intercept does.
Intercept does, yes. So the question perhaps is, why do we need this entire stuff at all? Why do we need L values and R values? Well, the thing is, we don't really need them. We could just say, okay, every time we require an L value, but instead someone supplies an R value, we just create a temporary variable for that, and we have an L value. But the thing is, there's some problems with that. For instance, if you have something like 4 equals 42 in a language like that, what would that do? Would that create a temporary variable for 4 and assign 42 to it? Does that change the value of 4? What if you write that a second time? Do we create a new variable? Do we use the same? It's like the semantics of this are very unclear, and there's not really anything useful you can do with that if you're trying to assign to an L value. And that's not the only reason. The other reason why we have this distinction is that in the case of something like a plus b, where a and b are both integers, the result by default simply isn't in memory. It's only in a register. So you could say, and it is in fact the case, that this distinction also attempts to model the underlying hardware, in that things that are R values are often things that tend to not go in memory and are just in registers. So even though this is a higher level concept, if you will, it's actually fairly low level. Higher level languages don't really need to care about L values and R values that precisely. Now, we've mentioned that and that goes back to your question, Lens. We've mentioned that L values occur on the left-hand side of an assignment and R values on the right-hand side of an assignment. Now, the second part of this is definitely true. R values can only ever be on the right-hand side. You can't assign to 42 or to 4 or to another number. But the other case is a bit imprecise, because you can have something like this, where we have two variables, we bind a reference to them, then we can assign these to each other, and then suddenly we have L values on both the left-hand side and the right-hand side. So what we could say, but this is something that C++ actually doesn't do, what we could say is L values can simply go on both sides. That's not what C++ does. Instead, what C++ says is that if an L value is used where an R value is expected, that L value is implicitly converted to an R value of the same type. And that's called L value to R value conversion in the standard. And the semantics of this is the standard specifies, for instance, that the left-hand side of an assignment operator has to be an L value, and the right-hand side has to be an R value. So if we take this example here, J on the left-hand side is an L value, so that's fine. IREF is on the right-hand side, but it's an L value. So we convert it to an R value, that creates a copy, and then that R value is assigned to J. And for the compiler devs here, this means that L value to R value conversion is basically where you load the value of the reference. So by specifying where we need R values and where we need L values, we know when to load the value at the location that the reference points to and when to use the reference itself. Does that help answer the question from earlier?
That makes a lot of sense, yeah. So the variable itself, each use of it is an L value, and then the compiler will basically demote it to an R value in the cases where
Yes.
that's what it needs to be.
Yes.
Because an L value
Variable-
always has an R value, but not vice versa.
Yeah, an L value can always be converted to an L value of the same type, yes. Okay, there's one last case we need to talk about early on, and that's const references. Now, in C++, what we commonly teach is that parameters that are expensive to copy should be passed as const references. There is a good reason for that, and it's not just const correctness. Const correctness is typically the thing we teach, because that's easy to teach. It's easy to say, if it doesn't need to be modified, make it so it can't be modified, that reduces bugs, and that's true. Not that that's for nothing, but there's also another reason for that. We've established before that parameters are L values, because they're just variables, right? So let's take a look at this case. We have some function that takes in a string by value and prints it. And then we create a string and call print by value on this string. That is something you can do. It's perfectly valid code, but there is a performance problem here. Print by value doesn't really modify copy at all, because print doesn't modify copy, because why should it? So even though that's the case, we're still creating a copy here, because we're passing by value, and passing by value means we create a copy. Ideally, we would rather just not create a copy just to print the string. So instead of passing by value, let's pass by reference. Okay? This still works. And now we don't create a copy, because instead of copying S, we take a reference to S and then pass that to print. Okay, so that seems better than this, but there's another problem with this. What if we want to print a temporary, meaning an R value?
Xcatalyst T0 says, but Cap'n, wouldn't indirect reference be slower if the struct is small?
Correct, that's why you pass small struct to value, but I've said we teach to pass parameters that are expensive to copy as const references. Of course, you're not going to pass a string by an int, by const reference. String is expensive to copy because it performs a deep copy, generally. So we're only talking about types that are expensive to copy. For things that are not expensive to copy, you just pass by value, obviously. But we're talking about things that are expensive to copy. Now, back to this. We've just looked at this code. This passes by reference. What if we try to pass a string returned by a function to it? So our print by value function, that works. We're just taking this value, copying it in. But there's a problem with this one, where we pass by reference. As we've established before, a reference can only bind to an L value. We've also established that a function that returns a value or a call to such a function is an R value. So here, in this call, we're trying to bind an L value. Sorry, we're trying to bind a reference to an R value. And that's not something you can do. So this code will not compile, because this is an R value. So there's a problem here. We would very much like to pass by reference, because we don't want to copy. But if we pass by reference, we suddenly can't pass in temporaries anymore. We'd have to do something like this, assign it to a temporary variable, and then pass that in, because now it's an L value. But this is fairly annoying. If you have to do that all the time, that gets pretty annoying. You don't want to do that. And also, this is not ideal because of other reasons that we'll talk about later regarding copy elision. But just in general, this seems very janky. There's got to be a better way of doing this. And there is. There's also another reason why this seems pointless. The thing is, the reason why is because we have a string here, and string is a value of class type. Note that in C++, class type means enum, but struct, class, and union. So even if it's declared as a struct, it's still called a class type. So class type doesn't just mean classes, it means structs, classes, unions. Now, at least with integers earlier, there was the argument that integers are typically in registers, so the sum of two integers is also going to be in a register. But with strings and class types, that doesn't really make sense, because you can't fit a string in a register, in most architectures at least. And you can't just load a string into a register. No, a string can only really reside in memory. Which means that even though this is an R value, it still kind of has to be in memory. Which is a bit of a weird situation. You can already see how the pre-C++11 semantics don't really work out too well in some cases, because we've said L values are in memory, R values are not, but all of a sudden R values of class type kind of have to be in memory. Like physically, maybe logically you can treat them as though they weren't, but physically they sort of have to be. So, because of that, well, actually, let's take a step back. R values of class type behave like they're in memory, but they're not L values. And it turns out if you think about that a bit more, they're actually sort of similar to something else that we've discussed before. Like, they kind of remind you of non-modifiable L values, don't they? Because you can't assign to them, that doesn't make sense, but they are in memory, so you could probably take their address. And that's what C++ allows. I got a bit lost here, hold on. I was talking faster than I was reading. What was my structure for this? Yeah, and since reference binding is the same as taking the address of something, if we can take the address of something, because it has to be in memory, we can also bind a reference to it. So, as a side note, that doesn't mean that R values of class type are actually non-modifiable R values. They're still R values, they just behave similar to them. And this is where const references have come in. A variable of const reference type is a non-modifiable L value, which means it basically models more or less the semantics of an R value of class type. Because of that, C++ allows the following. A normal non-const reference can only bind to L values, but a const reference is allowed to bind to R values as well. So with that, we can rewrite this function to use a const reference, and now we can take this temporary, this R value, we can bind a const reference to it, and we can print it without having to create a copy. So to recap this a bit, because this, I feel like may be a bit confusing. So we have L values and R values. L values are in memory. R values are not. However, that second part is only partially true, because class types sort of have to be in memory physically. So what we can do is we can treat these values of class type. Since they are in memory, we can still bind a reference to them. It's just that trying to mutate them would be a bit confusing because, again, you can't assign to for or anything. So we allow everything except that you can do with an L value except mutation, and const references happen to model this, so we can use const references for this. And this is, if this seems a bit strange, it is a bit of a hack, sort of. Const references just happen to align with R values in such a way that you can use them for this. It's a convenience feature to allow passing things to functions without having to copy them, so long as you're not mutating them. And if we look at this here, at least within the if we take a look at the lifetimes of this, in C++, the way this works, the lifetime of an argument of a call ends after the call returns. So the lifetime of this string here, returned by return string, it's alive until after print cref returns, which means that for the entire duration of while we're in the body of cref, of print cref, it exists, it has a lifetime, it is alive, it is in memory, so in here we can treat it as an L value. So that's another motivation of allowing this binding const references to R values. Again, mutating them, it would be dubious, but for at least a temporary duration, we can treat them like non-modifiable L values. Does this make sense, or are there any questions about this? Because this can be a bit confusing.
So,
Actually, well, go ahead.
no, you go ahead. Yours is better.
Okay. I'm not quite sure I understand why we can't mutate the R value. Like, why can't we mutate? Why can't we get rid of the const and maybe mutate the R value?
The reason why we're not allowed to do that is more or less by design, and the reason for that, or one reason for that, is that the semantics of that are a bit confusing. Because what happens if you assign to something like for? What is the semantics of assigning to this? What does that mutates the underlying object? Sure, but that's not particularly useful. What someone's saying is you can const cast, don't do that. In this case, I'm not sure it would be undefined behavior, but it would be a very cursed thing to do. You might get away with a const cast here, but that's not something you should do typically on that node. But yeah, the idea is basically that treating them like non-modifiable L values makes sense. But the thing is, if we just allowed reassignment as well, then we'd basically turn R values into L values because they'd have the same properties as L values, and we don't want that.
Okay. Thanks.
Yeah, so the reason for that is because const references don't allow mutation, we get rid of that confusing case of what does 4 equals 42 mean.
Yeah, but that's for like class types. But that's actually for things like integers. Yeah, if you assign to them, that's going to be confusing. But for things like strings, you can I don't see why we can't modify them and use the modified version.
Yes, but another reason why this is done is also partially for consistency. We have an example of that here. Yeah, because const references binding to R values is not just allowed for class types, it's allowed also for any type.
Oh, okay.
And so for consistency, because especially in templated code, it would be pretty annoying if suddenly the template failed to compile because you're binding a const reference to something that happens to not be a class type. That's actually something I was getting to. I'm going to finish this section real quick. Again, we allow binding const references to class types because class types have to be in memory anyway. Now, there are a few problems with this approach that we could see. And the first thing I've already addressed is if this is a temporary value that's about to basically die after this expression, doesn't this create a dangling reference? Well, in here it doesn't, because again, for the entire lifetime of while this function is called, the value is still live. So we don't have to worry about dangling references in this case. And we can simplify the semantics of this so that we don't have to worry about dangling references at all. and make it so that in any case, if we try and bind a const reference to an R value, the lifetime of the R value is extended to match the lifetime of the reference. So basically in here, we're binding this R value to a const reference S. That does not create a dangling reference. Instead, the R value, the lifetime of the R value is extended to live until S goes out of scope. And that only applies to const references because, again, we can't even bind R values to non-const references. And L values have their own lifetime already, so it doesn't apply to them. And in C++11, I believe this is a part of temporary materialization, more or less. And you can think of it in that way. The lifetime of this temporary value is extended to match the lifetime of this, so we don't create a dangling reference. And finally, for consistency, we extend this case with const references to apply to R values of any type and not just class type, simply for consistency. Which means that we can also do this, which under the hood creates a temporary variable to hold the value for. And the reason why that is useful is, again, in templated code and for consistency. It would be weird if our code suddenly broke because we're passing in an int instead of a string or something. We don't want that. So for consistency, we allow this. And that's another reason why we only allow binding const references and not regular references. Because regular references are modifiable. So if we allowed this with regular references, what would this do? Would this just create a variable? In which case, why don't you just create a variable? Like, that would get a bit confusing. Like, if you allowed binding int references to for, what would be the difference between creating an int reference, x, that holds for, and just an int that holds for? Now you all of a sudden you have this other way of declaring variables that's different from normal variables in exactly what way? It's just that there isn't really much of a use case, it turns out, for passing a modifiable, or rather binding a modifiable reference to an R value. Because in this case, if it's a regular variable, you could just create a variable. And for a parameter, well, modifying this doesn't really make much sense because this thing is about to expire anyway, if it's an R value.
Ooh, that's a good point.
The thing is that binding an L value reference to an R value, semantically, if you think about it, there isn't much of a use case for it. Now, of course, it should be noted that this is what C++ has chosen to do. You can always create a language that just allows binding references to R values, which just always create a variable under the hood. But then you have to answer questions such as, what happens if you do for equals 42? Do you allow that? Do you not allow that? What are the consequences of that? Have you thought about what the consequences of that are? In generic code, perhaps? I haven't, not in depth, but I'm pretty sure the designers for C++ have thought about this for a while, and what they come up with is this entire system. Now, of course, if you still feel like there's some weirdness in how L values and R values are handled, particularly with the thing that R values are not in memory except for when they are, if they're class types, there is a reason why the system was overhauled in C++11. So we're going to get to that now to answer the questions. But before that, I think there's a question here in Discord. Is then passed to then to pass the value, the function just takes a pointer to the temporary.
I think he's talking about like under the hood, it creates a local type of thing.
Yeah, under the hood, it does something like that. Yes. Yeah.
Mostly local.
We were talking about
So-
stack pointers.
Before we get to C++11 and to how this is overhauled, are there any questions about L values, R values, const references, or the reason behind that? And especially, is it clear why we have all of that? Because the point of this entire talk is kind of to explain, if we can call it that, is to explain the underlying motivations for all of this. We're not going to go into the exact nitty-gritty details of how everything works in the standard because we'd be here for a few days if we did that. Like the standard
Right.
also assumes that you know all of this already when you go into reading it. It just uses terms like R value and L value and expects you to understand the underlying motivations for why this is the place, and that's what I'm trying to explain here. So are there any more questions about this?
That makes sense. You keep taking questions. You can move on. I'll be right back. I got to use the restroom and get some more water.
Okay, sure.
Local, I trust you. You're the moderator. It's all in your
Okay.
hands.
What am I
I'm
moderating?
gonna
Everything?
check in. I'm gonna check in.
Everything. Yeah. What did you say?
I'm gonna answer questions in Twitch until you're back, because you kind of need to. The next part is important. If you miss that, nothing's gonna make sense.
Okay, I'll be quick.
There's not a whole lot of questions in Twitch chat right now. They're just complaining
Oh.
about C++ and wanting us
They're
to
just
move to
complaining
Rust, and I'm
about
like,
C++.
stop.
I see how it is.
Don't
This
engage
is
with the
Rust
trolls. This is a C++ stream.
C++ stream. I can't ban them on Twitch though, so I have to engage with them. I'm trying to have a good discussion. If the discussion falls into not a discussion, then I'll shut up.
Mm-hmm. Right. Oh yeah, local, because I said we're gonna be here all night. The next part is the big one. This
Yeah.
part is kind of the introduction.
Oh
Next
yeah,
part is
no,
the
this
big
didn't
one.
feel like the meat and potatoes. This was the I can smell it in the kitchen. The kitchen's
Yes,
about
yes.
to happen.
Now we're going to be talking about the real stuff, and after that, forwarding references kind of ties everything together, more or less.
Yeah, I've just been in Twitch chat. Like, we've got at least 3 very good reasons to be using C++ and not Rust.
Yeah, sure.
And so I think that discussion has finally died down.
Okay, that's good. That's good.
One of them, none of us know Rust. The second one,
Yes,
you're
that's a big
incredibly
one.
good at C++ and not Rust.
like
The
to
third
think I'm
one,
decent
we don't
at
want to
it,
write Rust anyway.
yes.
So I think that about covers it.
Okay, just to confirm one more thing. So when you
Yes.
say something like const int reference x equals
Mhm.
4, what actually happens is there's a temporary variable, and then the x, and then the reference binds to that temporary. Is this how it works, or am I missing something?
Under the hood, it's essentially yes. So what this does, it creates a temporary variable, stores 4 into that, then the const reference is bound to that variable, conceptually at least, yes.
Okay.
Which is again another reason why we don't allow L values to us. Sorry, I keep already going to the next part. Why we don't allow binding non-const references to just 4, because that would basically just be identical to a regular variable, and then you
Yeah.
suddenly have 2 types of variables that are sort of the same but sort of not. That's like, ugh.
Yeah, that part makes sense.
Someone's linking a Godbolt link to. Interesting. Let's see. Yeah, well, what Clang does under the hood, yeah. Sure. The thing about this is also what I mentioned. This is less about how things actually are implemented by a C++ compiler under the hood.
They're more convenience.
It's more about like the motivation behind it, because of course this is going to be somewhat imprecise when it comes to the actual implementation of or detailed inner workings of all of these things.
Oh, good.
Yeah, Clang does what I say. I'm not surprised, because the way compilers generate code is they typically do the stupid and simple thing that works, even if it ends up generating a lot of duplicate code, because the optimizer just gets rid of that. So what, for instance, a compiler will do if you pass if you have a function that takes a parameter, it will allocate a local variable for the parameter, store the initial value into it, and every time you use the value, you load it back out. Because that way, code generation is nice and simple, and optimizations can actually make the code decent. Yeah, and as Maddie is saying here on Discord, after optimization happens, you're not exactly able to have any idea what it does, which is fine. That's as long as the compiler has an idea what it's doing and it's correct, then that works. There's also a thing about optimizations. It's explicitly stated that by the standard that an implementation has to behave basically as though it did everything exactly like the standard, and so long as all these side effects are the same. So that means that a compiler is allowed to do something that is equivalent but faster, even if it doesn't do exactly what the standard says.
So long as anything observable remains the same.
Yes.
By whatever definition of observable the standard provides, we have
Yes,
to clarify
observable,
that.
I'm pretty sure, means calling a library function or accessing a volatile L value or stuff like that. So it's not a lot that it considers to be a side effect, but the thing is because if printing is a side effect, then every function that prints also has a side effect, so that kind of cascades that way. Yeah, for also what Maddie again on Discord, for debugging purposes, if it deviates too much from what you expect, it will be confusing. Yeah, that's unfortunately always the problem with optimizations. Like trying to debug optimized code, I wouldn't want to do that. I've had to do that in some cases before, particularly where I was like debugging CodeGen. It's not nice because your code is just something. You have to figure out what the hell the compiler did.
Yeah, a debug build is never gonna like you're gonna get what you get. I don't know how to anyway.
Maybe you can use like LLVM IR to debug instead of like actually checking the assembly. But if the problem is in the code gen, then it sucks, as you said.
Yeah. Ideally, you'd always debug IR instead of assembly. That's also what we do when we, or at least what I do when I work on Intercept, is if there's a miscompiler, always look at the IR first, because it's easier to reason about that than whatever the register allocator did.
Yeah.
Or whatever each instruction selection did, and so on. Lens didn't mute his mic, so I still don't know if he's back. I'm guessing not. Oh, because locally you mentioned something about tagged units and pattern matching. That, I think, is one of the main weaknesses still of C++, that it doesn't have pattern matching.
Yep.
Because Switch is pretty poor for a lot of reasons.
Yep.
It's also a 50-year-old construct, so that's not particularly surprising, but
we don't need fancy patterns for the compiler anyway. We just need to know what singular type we have. So our tagged class system with fancy casts is totally sufficient.
yeah. And the thing is, there are pattern matching proposals for pattern matching. There are pattern matching proposals, full stop.
I can't imagine those ever getting accepted in the next decade, though. That sounds complicated as hell.
They are working. I would be hesitant about seeing if they're gonna get into C. I'm not sure they'd get into C++ 26. That's like the maybe, but probably 29 at the earliest, unless they're like really close to. I don't have too much insight into exactly how far the committee is with things, but the proposals are definitely progressing and being considered. And there's also more and more talks about them. So we're gonna see it at some point, but I can't really pin an exact date on it. But I would expect within a decade, probably within a decade, honestly.
All right, so
If it takes longer than that, it would be a bit sad, honestly. And also, someone's used standard variant. Yes, standard variant is what you get if you try to implement tagged unions at a library level and not at a language level, which it's not pretty. It works for very simple cases, but anything more complicated, or if you need to use it repeatedly, standard variant is a pain, simply because the main thing that is missing is pattern matching, and that just makes working with it incredibly tedious. And it's regular C-style unions in C++ are a nightmare, not just because they're unsafe, but because they're unsafe, they're also very hard to deal with. For instance, what should a destructor of a union do by default? It doesn't really know what it is. What should it do? The answer is it doesn't do anything. You have to implement it yourself. If you have a union that contains a value that has a non-trivial destructor, something like a string, then you have to implement the destructor yourself, and the same thing goes for copying. I think copying is just copying might even be I'm pretty sure copying is definitely deleted if the thing has a copy constructor. I'm not sure what happens if it doesn't. I don't really use unions in C++ that much, naked unions at least, simply because they're like a pain to deal with. The standard variant is the closest thing you have to a tagged union, but because it's at the library level and not at the language level, the language doesn't really have a good way of supporting that. And at least if we get pattern matching, standard variant is still not going to be ideal, but it or any like variant-like type that you would write yourself could then just use pattern matching. Because there's also one thing that I like about C++ is how... Oh, hello, welcome back. I'm just finishing talking about pattern matching real quick because someone asked about that, or mentioned that rather, local mentioned that real quick. The nice thing about C++, typically what I like about it is that features are basically, I don't know how best to put it, but they can be reused. Like if you have something like an algorithm that operates on an iterator pair, you can define your own iterators to go with that. It's not like in many other languages where this thing is hard-coded, it only works for this built-in type. In C++, most of what you can do, you can do with your custom types, like range-based for loops, for instance, and the same extends to pattern matching. The pattern matching proposal also allows you to define your own things that you can match on. Anyway, Lens is back. I think we can get started with the next part, unless anyone has any questions now for that one. If not, then we can move on. So, to recap real quick, we've established that there's a difference between L values and R values. For literal types, that difference is very clear. And literal types is things like integers, floats. That distinction makes perfect sense. If they're variables and things like that, they're in memory. But if they're just values, like the literal for, that's not going to be in memory, ever, typically. We've noticed that there's some weirdness going on there with class types, because R values of class types, they are R values. It makes a lot of sense to still consider them R values. They do occupy memory out of necessity, because you can't put a string into register. Register can't fit a string. Or you can't fit an array of 1,000 ints or stuff like that. Like, things just get too big to fit in a register no matter what architecture you're in. So, meaning that these R values of class type are somewhere between R values and L values, sort of. They're similar to non-modifiable R values, and we can use, because of that we can use const, or because of that we've said that we can, and we've defined it, we've made it so we can use const references to quote-unquote materialize an R value and turn it into something we can take the address of. So, in other words, we can actually distinguish between two kinds of R values. Just the term R value is not enough. There are R values of literal type, which do not occupy memory, yeah. And R values of class type, as well as these materialized temporaries, such as if you bind const int something before, that do. So, and since C++ 11, this former kind is called PR values, meaning pure R value, and the latter are called X values, meaning expiring values. And the term R value is redefined to mean something that's either a PR value or an X value. So this R value category is kind of split into PR values and X values. And before anyone who knows C++ well says something, this definition is not precise. This is we'll get back to the actual definition of X values and PR values. But for now, the idea behind them is that there are R values that are in memory, R values which are not. Okay? So, the reason why it makes sense to introduce these X values is the following. Apart from things like confusing semantics such as assigning to for. L values typically are longer-lived objects, such as variables, and they're probably going to be used several times. Like this is not a precise definition of anything, this is an observation that we can make if we look at programs. Variables, if you have a variable, you're probably going to be using it multiple times. And they also live for the entirety of a scope. However, R values typically are just reused once. They're also reused immediately where they occur. Like if you have if we had this return string function earlier, this is just used immediately. It's passed to cref. After that, it's gone. It doesn't live for very long. And we have an example of this here. If we create two variables, we can do stuff with A and B. We assign them to each other. We do more stuff with A and B. That's how you typically use variables. And this thing is also that they expire immediately is also where this name expiring values comes from, by the way. I'm jumping a bit to and fro here. I apologize for that. Now, let's take a look at this code. Why did I put this here? Well, here we can see we're assigning B to A. Okay, so what? We're creating a copy here. In this case, that copy makes sense, because if you look at the comments, I didn't just want to write out an entire program, so I just kind of pretend that in here there's code that uses both A and B. Since the code after this assignment uses both A and B, you kind of need to copy B into A, because B is still used after that. Does that make sense? Why we have to copy here? Yeah, so the reason why we are copying B here is because so we want to copy A and B. Let's just we need to set A to the value of B. That's like kind of the presupposition, if you will. This code does something with A and B, then it has to set A to the same value as B, and then it has to do more stuff with A and B. But if we still need B, we still have B needs to keep its original value. We just need to overwrite A, so we need to make a copy here. So that makes sense, this code. At least under the assumptions that this code makes, the copy here makes sense. However, let's compare this here. Instead of assigning B to A, we're assigning a string to it. So now the situation is very similar, but the thing is the value, the R value, that's returned by return string, we don't need that anymore here, right? So why would we still copy it? It doesn't make sense. Why would we want to copy return string if we don't need it anymore afterwards? Why wouldn't we just use it directly? For instance, the way strings are implemented is they typically have a data pointer that points to the heap if data is sufficiently large. What we could do here is we just copy the data pointer, we make a shallow copy, and then zero out the temporary so that its destructor doesn't delete the data. And side note, by the way, for the people that know C++, don't mention copy elision here. We're going to come back to that later. For now, just pretend this makes a copy.
Well, what about copy elision?
We're going to talk about copy elision later. Like, the motivation here is we don't want to create a copy in this case. So how do we accomplish that? So instead of copying, we want to move the value from here to here if it's a temporary. And that pretty much is true for all temporaries. It's not just in this particular case. If we assign a temporary to something, we'd rather just use that temporary value directly instead of copying it and then throwing away the original immediately. That doesn't make sense. Why would you copy it if you're throwing it away immediately? The original it is. So we can see that there's a distinction here, a fundamental one, that in here B we have an L value, here we have an R value. And if we look at what we just said, we can sort of paraphrase this and say, if we have an L value, we typically want to copy it, because chances are that if it is an L value, we're going to be using it later, because L values are longer lived, right? However, if it's an R value, there's no way that this is going to be used later on, so we might as well just move it, meaning L values should be copied, R values should be moved. Does that make sense? Because that's the fundamental insight here. L values should be copied when they're used, R values should be moved because we don't need them later. Now, and as a reminder, R values includes both PR values and X values.
Wait, one quick question.
Yes.
It doesn't. So when we call return string, doesn't the data get deleted after the call to return string ends?
R value, once this
Yeah.
expression is done executing, the
Yeah,
destructor
so
of this will be called. Yes. But that's why
yeah,
when we
so
move,
you cannot
we zero
copy.
out the original object so that its destructor doesn't delete the pointer that we've copied.
Oh, okay. I didn't know that. Okay. Okay.
That is
So
important.
the structure doesn't get called L.
It does get called, but there's nothing to
It does.
delete because the move
Exactly. It does
removes
get
that
called,
data.
but it does nothing. Yes.
Oh,
Because you can write
okay.
the
That's
constructor, you can write the destructor in such a way that it checks if the pointer is null, and if it's null, it doesn't delete it. And as a matter of fact, if you delete a null pointer, that's a no op. It doesn't do anything. You can do that. That's perfectly well defined. It just doesn't do anything. Just like free. You can just write delete pointer,
okay.
and by setting it to the null pointer, you're making sure that it's not going to get deleted. In this particular case.
I can post a really simple example in the text chat for Discord because I can do images. You don't have to know what most of this does, but just note that other scope equals null pointer is removing the first scope from the other object that we're moving. So when the
I'm pretty
first
sure-
right, so the descriptor is then checking, hey, do we still have a scope? Because if we do, we can remove it. If we don't, then we probably got moved.
Yeah. I have an example of this later on, but
Yeah, you'll have a better example. I just off the top of my head I had
I
that.
so
Thanks.
yeah. We just discussed this. L values, we want to copy them because the L values, by its virtue of being an L value, will probably outlive that particular use of it, whereas R values can't really outlive the context they're used in. Because they're R values, they only exist for so long as they're needed. So R values should be moved. Okay, we already have const references which can bind to R values, but there's a problem with that. They're const. We can't modify them, which means we can't move from them. We can't use const references for that. We can also not use just regular references for that because those can't bind to R values. So what do we do? Well, to facilitate moving, C++ has added C+11 added a second kind of references. And these are the R value references. R value references are written with 2 ampersands. So a string ref is an R value reference to standard string. And regular references, as we've been calling them, are renamed to L value references. L value references are just the same thing as the references we've been talking about the entire time, except that now they're called L value references to distinguish them from R value references. L value references haven't changed. They can still only bind to L values, except that a const L value reference can also bind to an R value, as we've discussed. So their semantics are the same. And the semantics of R value references are analogous to L value references. L value references can only bind to L values. Therefore, R value references can only bind to R values. An example of this here. We have an L value string. This L value reference can bind to this L value. And this R value reference here can bind to the R value returned by return string. If we try the opposite, that doesn't work because we can't bind an L value reference to an R value. And we can also not bind an R value reference to an L value. Now, this is a restriction that we've discussed before. There's a reason why that's necessary. And this is by design. This is quote unquote an arbitrary decision, but except it's not. There is a good reason for why we do it this way. But note that that reason why R value references can only bind to R values is because we've defined that they can only do that. So in and of itself, this doesn't seem too useful. But where it gets useful is that C++11 added the capacity to overload based on L value versus R value references. So now you can do this. This overload, which takes an L value reference, is called if it's passed an L value. And this overload, which takes an R value reference, is called if we pass an R value. The most prominent example of that is the move constructor, as well as the move assignment operator, which were also added in C++11. So here we have an example struct, which is what we were discussing earlier. It just contains an int pointer, that's the data, whatever that is, and the size. So very primitive. I've omitted even the regular constructors here, like pretend this has other stuff to make it actually useful. I've just included the things that we need to talk about right now. In here we have the copy constructor that takes a const reference. This has been in the language for a long time. That's nothing new. In here we just create a new, if you don't know the syntax, this just creates a new int array with this size. Then we do a mem copy to copy over the data. So this just copies the data. And now, in addition to that, we also have a move constructor that takes an R value reference to S, and what it does is it does exactly what we've described earlier. If it's an R value, we move it, meaning we copy the data pointer and zero out the data pointer over the original object. So then when we delete it, when we delete the original, the data that we have is not going to get deleted, because delete array null pointer is a no-op. So we don't even have to check if it's null pointer, we can just do this. So again, to recap, because this is the central part of this entire discussion here, we've observed, this is an observation that we've made, and not in a very general one, that L values are typically longer lived, used multiple times. So if we assign them, if we use them, we need to copy them because we still need the original. However, R values don't live for very long. They're typically immediately reused, or rather immediately used and only once. Which means instead of copying them, we can just use that value, basically steal it, because we don't need the original anymore after that, because the original just gets destroyed immediately. So because of that, because L values need to be, we need to preserve the original for L values, but not for R values, meaning we need to copy L values, but we want to move R values. With this capability of overloading based on whether something is an L value or whether it is an R value, we can do different things based on whether it's an L value or whether it's an R value. Or to put it differently, or rather to paraphrase that, we can do different things depending on whether we need to keep the original or whether we want to just move from it, meaning we can do different things depending on whether we want to copy or whether we want to move. And that is the entire idea of how moving works. Now, yeah, this constructor is the copy constructor, this is the move constructor. Why does this, I think I need to do that, well, now this is centered. Okay, and this is the important thing to realize here. The fact that move constructors are used to move the value is a convention. That's all it is. Because we have introduced these R value references, because it makes sense to do that, because we've observed from how people write programs that this is the thing you need to do, so we introduced a feature to make it easier. We could just as well define a move constructor that does something like this. It just prints 42 and does nothing with the data. You can do that. This is legal C++. This will compile. It will print 42. It's probably it's not really useful C++. So again, the fact that move constructors move, it's nothing intrinsic to move constructors. It's because we've written move constructors in such a way that they move. That is why they move. We've introduced R value references with the intention that people use them to mark that something should be used. Because R values are something that typically should be used, we made it so that R value references can bind to R values. Does this make sense? Is this clear? The fact that R values should be reused immediately is something that's intrinsic to R values. But the fact that R value references are used for moving is a convention that's motivated by the fact that R values need to be reused. Does that make sense?
Yep.
Because that's the most important thing to understand about moving. Okay, so how do we...
Okay, so when... Okay. Should I ask the question later, or...?
This is good.
You can ask it now. If it doesn't make sense for now, I'll explain it later.
Okay. So when we pass like an R value to an L value, is the move constructor automatically called? Is it always going to be called?
If you try
like
to
when we did the A equals return string above.
I'm not sure exactly what situation you're referring to, but if you, for instance, if this overload is the only one that existed, and you tried to pass an R value to it, that would be a compile time error, because you can't bind an L value reference to an R value.
What about the string version? It's just above. If you scroll up a little bit.
Yes.
Yep. No, just above the previous code slide. Yep. Is the move constructor called here? Or do we make a copy? Yep.
So yeah, that's... I should really tie back to that. That's a good point. Yes. So with the knowledge that we now have, let's analyze this, shall we? What is this? This is an R value. Why is it an R value? Because we've previously established that functions that return a value, a call to such a function is an R value. So this is an R value. Assignment operators are just overloaded operators class type. So this will call the assignment operator with what is the type of this? Well, the type of this is it's an R value. So this will call the so-called move assignment operator, which is defined to take a string ref. Yes, this will move. It doesn't call the move constructor, but it calls the move assignment operator, which is something similar.
Oh, okay. I see.
Pretend they're the same thing.
The reason why it moves is because now, starting with C++11, the standard library, the string type, has defined an operator that takes a string, an R value reference to string, and moves from it. The reason why this now moves is because now we have a way of specifying to overload based on R value. Now we have a way of overloading based on R valueness. So they've added an operator that does exactly that and moves if it's an R value. Does that answer the question?
Yep. Thank you.
So, again, you can do, it's a convention. You can do this, don't do it, but you can. So the fact that the move constructor moves, again, I'm reiterating this again because this is the most important thing to realize. The fact that the move constructor moves is not because it's a move constructor. It's because move constructors are written this way out of convention. Real quick, off topic, because Maddie mentioned standard exchange. That is a nice trick you can use for things like that. It's It's often used for move constructors to simplify implementing stuff. Yeah, standard exchange. Now, yeah, again, that's here's just this paragraph is just reiterating what I've said. The reason why R value references are associated with moving is because they tend to bind to things that we want to move from. And using R value references to represent moving is a convention that makes sense, but it is a convention. Now, moving these temporaries is already pretty good. It's definitely something we want to do. However, there's another case that we want to consider. We take the example from above, we modify it a bit. Suppose that after this assignment, instead of us still needing A and B, suppose we don't need B anymore. We're still copying B here though, because it's an L value. But we don't need B anymore, so why do we copy? Well, ideally, we'd rather not copy, we'd just do the same thing. We want to move B into A. B is an L value. How do we move it? Well, what we can do is we can turn B into an R value. So how do we do that? We can cast it to an R value reference. It's valid, you can do that. And what this does is this effectively turns the type of this into R value reference to string. And an R value reference, because it's an R value reference, is an R value. Which means what this cast actually does is it tells the compiler to treat B as though it was an R value. Not just as though, it converts it to an R value. And note what this cast does. Under the hood, of course, this cast is a no-op. The only thing this does is changes the type of B in this expression to be an R value reference to string. Yeah, that's also important. The cast, this is just a matter of convention. The cast doesn't do anything to B. It doesn't actually, quote-unquote, convert it to a temporary. What this cast does in this case is it tells the surrounding code, in this case the assignment operator, the surrounding code is suddenly handed an R value reference. And because we've written that code in such a way that it assumes that an R value reference typically represents a temporary, or more precisely, that an R value reference represents something we should move from, this code now performs a move instead of a copy, because it invokes the move assignment operator. And I'll reiterate this again. Most important part is because we've written our code to move when it sees an R value reference, casting to an R value reference invokes the code that causes a move. In and of itself, the cast does nothing. The code that's surrounding the cast is reacting to now suddenly seeing an R value reference, and it does the move. Since writing this cast, you've probably never seen this cast like this in C++, because people don't do this manually. This is kind of annoying if you have to write static cast all over the place, and you have to specify the type again, even though it already knows that it's a string, so that gets annoying. So instead, C++11 added a library function that does this for us, and you've probably figured out that this library function is standard move. All that standard move does is it returns an R-value reference to whatever is passed into it. This code does the exact same thing as this code, it's just shorter. Standard move casts to an R-value reference, and the surrounding code reacts to it and does the move. And this is also why we tend to say that standard move doesn't move. Because it doesn't. The surrounding code does the moving. Standard move, it's more accurately, standard move enables the move. Does that make sense, or are there any questions about this?
I understand. I don't
That
know
does
better.
make sense. It's just, it's so C++ like. It's annoying.
Mhm.
So
bit of a
standard move
roundabout
is
way
just a cast.
Standard move is just a cast, yes. It's just a static cast to R-value reference. That's all it does.
Of course. Of
Mhm.
course.
As a consequence of that, if you understand this now that you know, okay, standard move doesn't do anything, it just causes surrounding code to now select the R-value reference overloads. As a consequence of that, standard move is utterly useless if the surrounding code is not equipped to handle that move. For instance, if you have a variable and we pass it to a function that accepts a const reference, we can move all we want. It's not going to do anything. Because this const reference is going to bind to the R-value reference all the same. No move is going to happen in this case. This code doesn't accept an R-value reference. It doesn't know how to move. It just binds the const reference to it, and that's it. And you can use standard move all you want. It doesn't do anything. This is valid code because, again, const references can bind to R values. It just doesn't do the thing you think it does if you see this. It's also why if something is already an R value, standard move is also useless. So in here, the standard move is equally pointless because return string is already an R value. And sure, you can cast an R value to an R value all you want, but that doesn't change the fact that it's still going to be an R value. So instead of writing this, write code like this instead. That assumes, of course, that this returns a value. If this returned a reference, things would be different. But if this returns a value, there's no point in casting a function that returns by value to try to move that, because it already does that. That's also why repeated applications of standard move don't do anything either. They just have the same effect as calling standard move once. Right. So that's standard move pretty much done and handled. You now know how that works. So let's discuss R values a bit more, because we've been kind of being hand-wavy here with our definition of everything just to get the point across. Which the point, again, was L values. Typically, we don't want to move them. R values are things that typically should be moved, and that's why R value references are treated like things that should be moved. Now that we know how moving works, here's a few more points that we need to discuss, so that we are nice and precise and so that I don't actually tell you something that isn't true. We've mentioned that X values are R values that occupy storage, and PR values are R values that don't occupy storage. The thing is, that's not entirely correct. That's like the motivation for all of this, but from a definitional point of view, that's not entirely correct. The thing that we were referring to previously as R values in part 1, they are all PR values. And there is such a thing as a PR value of class type. So the actual distinction is not as simple as storage, not storage. No. And because of this, since we can't put a string in the register, and since there are PR values that are strings, that means there are PR values that, at least in the underlying implementation, occupy storage. The thing is, though, the way C++ handles this, if you try to do anything with a PR value, irrespective of whether it's of class type or not, it requires taking its address, so that actually requires a memory location. A temporary object is created to store the value. Those temporary objects are called X values. So, and this conversion is called temporary materialization conversion. In other words, a somewhat more precise definition of what we were talking before was values themselves are PR values, and temporary objects created from those values are x values. And even though this is now technically correct, it's still more of an informal explanation, because the way the standard works is it doesn't give a definition. This is what an PR value is, this is what an X value is, and from the definition, if you look at any expression, you can figure out what something is. No. The way the standard uses these terms, it provides a one-line definition in basic LVAL, but the actual quote-unquote definition of what is a PR value, what is an X value, happens implicitly all over the place. The standard in many places will just say the argument, for instance, the argument of an assignment operator is the right-hand side argument is a PR value, the left-hand side is an L value, and it returns an L value. That is how these terms are used throughout the standard. The reason why any given expression is a PR value is because the standard says so. There is no abstract definition of what is a PR value and what isn't. We might, in terms of terminology, we might just as well start calling expressions red, green, and blue, and say that the right-hand side of an assignment is red, the left-hand side is blue, and the assignment itself is also blue, and the standard wouldn't change if we just substitute them for colors.
The C# Roslyn compiler.
The reason why we use these terms PR value and X value is because there is an underlying motivation to them. That motivation is not how they're defined in the standard. The motivation is not wrong, but the standard assumes that you know the motivation, and then it uses these terms based on that assumption. And because of that, if you read the standard, it's not going to explain really to you what exactly a PR value is. In that sense, the standard is less of like a book that you can read, it's more like a dictionary. You don't read the dictionary typically. If you know a word that you want to look up, you look up that word. Same thing with the standard. If you have the question you need to answer, you look that up in the standard and it will give you a precise answer. But if you don't understand anything about what any of it is based on, you're not going to understand what it's saying. So again, the reason why something is a PR value is because the actual reason is because the standard says so. But the underlying idea why it would make sense to consider something a PR value is because of this thing with storage and not storage and so on. That's also not to say, again, that's not to say that this underlying concept is meaningless. It's just that the standard doesn't rely on that concept. These terms like PRs and X values are just labels, but the labels are motivated by the properties of real world, both hardware and software. To understand why the standard uses these labels in the way it does, we have to understand the underlying motivations, which is what I've been talking about for the past I don't know how long. Okay, and one last addendum. Temporary materialization conversion is one way in which X values are created. It isn't the only way. For instance, a cast to an R value reference type also yields an X value. Why does it yield an X value? Because the standard says so. So if you, for instance here, if you move something, this entire expression is an X value. Same thing with because it's just this, and this entire expression is an X value. And if you have a function call that returns an R value reference, that is also an X value. And since X values and PR values are both R values, R value references can bind to them and you can move from them. So if we wanted to give another definition of standard move, or rather a precise definition, standard move can be used to convert an L value into an X value. And that then causes the move. Does this explanation sort of make sense? I know we've glossed over some things here, and I'm not going to give a precise definition of everything that's an R value, that's a PR value, or an X value, or an L value. If you want that, you can look it up. CPP references a nice summary. The standard itself doesn't. Are there any questions about this part in particular? I also love local in chat. Is this Linux? No, this is a PDF. Yes, it is a PDF. I used LaTeX to make this, if someone is wondering. This is just a LaTeX document. And the app that I'm using, I'm pretty sure is the KDE document view, or whatever it's called. Just some PDF view, whatever is the default on KDE.
There's
That's the
like
real answer.
Foley going on
The
right
app
now.
is probably a PDF viewer. That's genius, local. I never would have figured.
Are we watching Lens? What is this? I'm here.
So I presume there are no questions. Do you understand this? Does this make sense? Because this can be confusing, this part.
It is confusing.
Okay, so one thing.
Go ahead.
Sorry, go ahead.
Okay, I was just gonna say it
No,
is
no, you-
confusing that basically. Okay, I just totally got sidetracked. That says explantation. Sorry. Informal
Does it?
explantation. It
Nice.
does. That totally distracted me. I just noticed that.
It does.
So the confusing part is like, why didn't they stick with, like, why did they have to just say the standard does it? Why couldn't they just stick with actual definitions?
That's not precise enough, unfortunately. Is the main reason.
Okay,
The standard
that's
is a formal, very precise document that has to exactly define this is the next one, because every we'll get to that, I think, if I haven't mentioned that already. Every expression in the language has exactly one value category, either X value, PR value, or L value. R value is kind of like an overarching category. It means X value or PR value. And the standard has to define for every expression what it is, because that determines how the code surrounding it behaves. And the problem is that a general definition of the term PR value, X value would just unfortunately end up being too imprecise. So instead, what the standard does is it just lists everything that is a X value or R value, simply to make sure that there are no doubts about it. Of course, you could very well ask, why does the standard not include a section that just lists everything in one place? That's a good question. It would be a good idea to add that to the standard. Definitely, sure. But it just currently just doesn't do that. There is a small summary on CWP reference, but unfortunately the standard apparently doesn't really like doing these sorts of summary too much. But yeah, but a definition in this case simply doesn't really work too well. And the thing is, defining it on a case-by-case basis is kind of like a definition. That's kind of how you define what a formula is in logic. You say, this is a formula, this is a formula, this is a formula, nothing else is. Same thing here. This is a PR value, this is a PR value, this is an X value, that's it. Does that help, sort of? Or?
That helps a lot. So because they're basically like, it's too generic. Like something in the future could come up that makes that not able to apply. Or even something that currently exists. So they're kind of scared. So they're like, we'll just specifically define it, but this is kind of why we're doing it this way.
Yeah.
Okay.
That's also if I point at any given expression and ask you, is this a PR value or an X value or an L value? You can probably tell if it's an L value or an R value, but whether it's a PR value or an X value is more of a matter of definition. It really is. If I say, what is 3 plus 4, and you say it's a PR value, you might have been able to deduce that, but the only way of knowing for sure that it's a PR value is you have to know for sure that it's a PR value because you've looked up that part in the standard.
Yeah,
again,
that makes
is
sense.
why I'm not going to start listing everything that's a PR value now. This is still, again, that's why I've been calling this an overview that explains the underlying motivation of all of this, because you don't have to know you don't have to precisely know whether something's a PR value or an X value or not. You don't have to remember all of that. It's much more important to understand what is moving, why do we need it, how does it work, that's important, how do we use it, that's the thing we want to arrive at, ultimately.
Yeah, that makes sense.
Okay, so that was just a more precise discussion of R values and X values. And one more thing, because I glossed over that for the purposes of explaining things, we previously mentioned that X values were introduced to reduce the number of copies. That's true, but even before X values were introduced, the standard already had the concept of copy elision. And that copy elision became mandatory in C++ 17. For instance, let's consider this code here. Syntactically, what this does is it takes a string literal, it creates a string from it, then takes that string, creates a string from it, and then it takes the string and assigns it to this string. So a very primitive pre-C++ 11 analysis would suggest, it's true. We would suggest that, okay, we create one string called foobar, we then copy that string into this string, and we then copy that string into this. Previously, we used that analysis that a equals b, or sorry, a equals return string that need x values, so that we use that analysis to justify x values. Now, the actual thing that x values are used for semantically is for moving. That's the main reason why they were introduced. This case is actually handled by something else, and the actual explanation of how that works precisely in the standard is a bit more involved. But informally, if we try to construct an object from a PR value of the same type, we just omit the copy. We use that PR value directly. So in this case, what this actually does is this creates a string. This would create a string from a string PR value, but nothing actually happens. We still just have one string. And since C++17, this syntax is also defined to perform copulation. So this assignment in a declaration and in a declaration only is not an assignment operator. It's the same thing as just putting the value right here in braces. So this also doesn't copy. So as a matter of fact, this code does the exact same thing as this code. It just constructs one string, no copying, no moving. There's one string and only one string. And that is guaranteed. That is not an optimization. The standard, since it was 17, requires that that is performed.
So,
Okay.
Gmail said, so we need more RAM to run this program.
This is important. The
Might have
code
to download
above
some.
this behaves exactly as writing this. And another important consequence is that if you have an assignment in a declaration, that doesn't call an assignment operator or either a copy assignment or a move assignment operator. It doesn't. It just directly constructs the thing. This is just syntactic. This is just syntactic sugar for this, basically. That's what's actually going on. So the initial reason that we gave for introducing x values and r value references doesn't really exist. Like the a equals return string case, that just does copulation, basically, in a way. The actual reason why we want r value references is for moving. That's the main thing they're there for. But the problem is that it's hard to explain moving without first explaining x values, so we kind of pretended copulation didn't exist. And if copulation really didn't exist, then x values would help optimize that case. Just so you know, there are two things that work here. X values for moving, and whenever you have a PR value, then it uses copulation. And there are forms of copulation. Also, there are forms of copulation of return values in particular that are fairly sensitive to what you're returning. And in general, copulation works on PR values and not X values. And we've established that the result of a move is an X value, which is why you should pretty much never write return standard move. Don't do this. Instead, just return the thing that you're returning and let copulation take over. So moving is better than copying, but neither moving nor copying, and instead just using the value is better than moving. So this is something, just know, don't write return standard move. There are cases where you have to write it, but in general, if it compiles without it, don't write it, okay? If this fails to compile, try to add the move and see if that works. There might be some cases where some operation is deleted where you can't do that, so you have to move. But in general, don't put standard move in a return. At least don't just put return standard move something. Okay? Just something to remember. Because this is a common mistake that beginners and intermediate programmers that are new to C++ make, is that they assume, okay, moving is better than copying, so I should move when I return, right? No. The language already has ways of making sure that this isn't too costly, that don't involve moving, and moving can actually just prevent copulation, so don't do this.
Interesting.
Yeah. I'm just saying, if you feel like you need to put a standard move on a return, you might have done something wrong earlier. Yeah, there are like weird cases where you have to do that sort of. Typically, if it compiles without it, don't put it there, okay? That's like the rule of thumb. If it compiles without the move, Don't use it in the return statement, that is. Okay? Now, some few more additional notes, and we're almost done with this section, don't worry. C++11 actually has 5 value categories, and that's the so-called fundamental categories. That's L value, X value, PR value. L value is pretty much the same from what we discussed earlier. Every expression has one and only one of these categories, and the standard defines for every expression what something is and what operands it takes. Also, what value categories its operands are. For instance, the right-hand side of an assignment has to be a PR value, which means that that's where L value to R value conversion comes in again. That's still there. In addition, there are 2 mixed categories, an R value is either an X value or PR value, and there's also the term GL value, which is a generalized L value. That is either an X value or an L value. So typically we illustrate this with this diagram. This is pretty well known. This is also just a screenshot from the standard. So every expression is either L value, X value, and PR value, and then just these 2 terms that are sometimes used because it's easier to talk about, to just say R value instead of X value, and for X values and PR values, or this is true if it's an X value or PR value. Instead, I would just say if it's true, if that applies to R values, that applies to GL values. So yeah, that is this taxonomy. Now, if you see GL value, that's just a term that refers to either of these. Now, one last note on, I think this is pretty much the last one now, on trivially copyable types. In C++, when we say copying, we mean deep copying. If you copy a string, you copy the data on the heap. Moving is sort of shallow copying and leaving the moved from thing in an empty state, such that when we call it destructor, it doesn't destroy the moved thing. So copying is deep copying, moving is sort of shallow copying. And the thing is, there are some types for which shallow copying and deep copying are the same, such as integers, arrays of integers, standard span, standard string view, and some other types. And these types are typically called trivially copyable types. The precise definition of trivially copyable is all of its members are trivially copyable, like either it's an integer or a built-in type like that, or if it's a class type, all of its members are trivially copyable, and it doesn't define a copy constructor or copy assignment operator. That's what it means to be trivially copyable. And that also means that attempting to move an int is not going to do anything to it. Unless if you have an overload that takes an R value reference to int, you can write something like that, but there isn't really a point in writing that, because you can't even define a move constructor for int or anything like that, so it's typically pointless to overload or something like that. There may be use cases, but it doesn't really do anything. Like, moving an int is the same as copying an int. And this also sometimes comes as a surprise to beginners, because if we look at this code, these 2 lines are very similar, but also very different. This allocates a vector of 1,000 integers. That's what this constructor does. It allocates on the heap 1,000 integers. This puts an array of 1,000 integers on the stack. And these 2 lines also do something very different. If we, I need to remember probably that, I'm not sure how well I've been remembering this, that the chat is down here, so I need to point up here always. If we take this vector and we move this vector up here, well, a vector has a data pointer, size, and capacity. That means we copy those, we shallow copy into vec and 0 out the other one. In total, we copy a pointer into integers. That's a total of 24 bytes copied. This here does something very different, because all of this data is on the stack. What this means is the array just copies the entire array. So this copies 4,000 bytes. Be careful here. Just because you write move doesn't mean it gets moved. It can only move it if that makes sense for the type. If shallow copying and moving are the same, it just does a copy. So because of that, it doesn't really make any sense to move an array unless the array elements are something that do have move constructors, and then you'd be moving those. But if you have an array of ints, then standard move on an array of ints, I would consider that just a bug, basically, because it doesn't do anything other than copying. You're making it look as though there was a move, but there isn't. Okay? Does this make sense here?
Don't write standard move for trivially copyable types.
Yeah, because it doesn't do anything. It's just noise in that case. It also makes it look as though there was a copy, as though there was a move, when in fact there is a copy. So it can make it seem like the code does something that it actually doesn't do at all. Because this doesn't move 1,000 integers, because that's you can't move an integer. You can the only thing you can do is copy it. So it just copies everything. So yeah, that's also why you'd also not move a string view, something like that, or a span, or an integer.
Oh, yeah. As Matty pointed out, there are templates for determining whether a type is
there
trivial.
are
trivially
type
copyable.
traits you can use in the standard library to query: is this trivially
Yes.
copyable? Is it trivial? Is it movable? Whatever. There are dozens of those that you can use for template code. Yes. So you
Why
can-
doesn't move use as templates?
Well, the only thing move does, it casts to an R-value reference. That's all it does. And the thing is, moving this doesn't hurt. It just doesn't do anything.
Well,
It's not like
yes.
this breaks your program or causes an error or does something different. No. The point of this line here is that this doesn't do anything differently. You're just writing noisy. You're writing move when it doesn't do anything.
But it's pointless. Yep.
It's just pointless. It's just pointless. The reason why you're not supposed to do this is just because it's pointless. That's the only reason we're not supposed to do this, because you don't. And the main reason is why you don't just write pointless code that doesn't do anything. That's like a very fundamental thing. And also for standard move in particular, when you see move, you typically assume there's a move happening here. You can't move an array, you can only copy it. So this kind of makes it seem like there's something going on that actually isn't. Instead, you just write this here. It's very clear that this does a copy.
Mhm.
That's why you're not
Okay.
supposed to write this here. It's not like this breaks anything. It just doesn't do anything. Same thing with
Okay.
writing standard move, like using it multiple times. It doesn't do anything either.
Yes. It doesn't.
Hmm.
So, what is that? What is our PDF?
Sorry, what?
What is the document?
This document
Oh.
here
Yep.
is something I wrote just for this.
It'll be like in the description,
general.
presumably, right?
Yeah, we can. How do you put a PDF in a description? I can put it on GitHub. Maybe?
No.
No.
What is the PDF about?
It's about value categories in C++. It's what we've been talking about for the past hour or so. I'm not
2
gonna-
hours.
If you've missed that,
Okay.
you're gonna have to unfortunately rewatch it, because I can't retrace all of that. I'm gonna give a brief summary at the end, but.
Okay.
Okay, so yeah, this basically just discusses what we've been talking about so far. Again, and also, yeah, this means you have to be mindful, because standard move isn't some kind of magical thing that just eliminates all copying from the program. No, the only operation that the type supports is copying. You will get a copy. Like if, for instance, a type doesn't define a move constructor, if you try to move, you're just gonna get a copy, unless in most cases. And there is if you're using Clang Tidy, it will warn about cases like that. Okay, one last note. This is a bit of a confusing one. This is sort of a technicality. Variables of R-value reference type. We've mentioned that variables are L values, which makes perfect sense in most cases. There's one case that tends to confuse beginners, and it's this one: a variable declared of R-value with an R-value reference type. Variables of R-value reference type are L values, because variables are always L values.
Yes.
S is declared as a standard string ref. S itself isn't a standard string ref. It only means S can bind to an R value or a standard string ref. Variables are always L values. Always. For instance, this call here calls this overload
I see.
not this one,
I
because
see.
it's an L value, not an R value.
Yeah, I see.
Which means if you want to call this overload, you need to move it again.
Yep.
So then, if you need to move it anyway, what are these variables good for at all? Well, an R-value reference variable is typically pretty pointless, but where this comes up very often is in parameters. If you have an R-value reference parameter that can bind only to R-values, as we've discussed, if you want to move from it, you need to call standard move, because this parameter is still an L value. It can bind to an L value, to an R value, but it itself is still an L value. And to move from it, you need to call move. Okay? So this is something to watch out for. Just because it's declared as an R value reference doesn't mean every time you use it, it gets moved. Now, you still have to move it explicitly. Okay?
Yeah, I see.
Any questions about this part?
Well, I have no questions, so I don't know about other people.
Okay, I will say if you have no questions, please try not to interrupt every other sentence, okay? Just something.
Okay.
Okay. The question is, does the ref mean this thing has no owner for the time being? No, the only thing this indicates is that this is a reference, and it's a reference that can bind only to R values. That's all this indicates. Okay? So, to recap kind of all of what we've just said here, before we get to perfect forwarding, originally, we made a distinction between L values and R values. We've then found that that distinction is a bit imprecise, and it led us to distinguish instead between X values and PR values, where X values are things that are moved. They're called X values because they're expiring values. That's where the name comes from, because they expire. We're moving from them. L values typically are longer lived, which means when we use them, we don't want to move from them. We want to copy them because we probably still need the original. R values, and that includes both PR values and X values, are things that are temporary and that are not going to be used anymore, that we want to just use once and immediately, which means we can reuse the resources. And in particular, PR values are R values that just intrinsically are R values. And X values are things that we made into R values, basically, by using something like standard move, in order to tell it that it should behave like an R value, which typically means that we want to move from it. Standard move, all it does, it doesn't move. It enables moving by casting to an R value reference, and the surrounding code responds to that and performs the move. Actual definition of these terms, you can check the standard for that. This is just the underlying motivation. And that pretty much covers everything we've been discussing. Oh yeah, we talked about copy elision, and there are some cases that are basically even better than moving, because they're no-ops, basically just uses the value without any copying or moving. We've talked about this value taxonomy here. Sometimes moving doesn't actually do anything if the surrounding code is not equipped to actually do any moving. Because again, moving in and of itself doesn't do anything, it just enables more efficient overloads to be called. Then this particular case here, because that trips people up sometimes, variables of our value reference type are still variables, and thus they are still L values. Okay, that's sort of a quick summary of all of this. Any more? I'm going to ask one more time. Any more questions about L values, R values, moving, R value references in general, or any of that? In particular, is it clear what standard move does, how it works, why it works the way it works?
It's at least clear what it does, and it's somewhat
Mhm.
clear why it works the way it works.
Mm-hmm.
And I think the answer is like I should just never use it.
No, the point of standard move is that you use it as often as you can.
Right, but like my instincts would be like, oh, use it when I'm returning from a function. But like I should instead use it for parameters of a function, right?
Yes, when you're moving, yeah. When you're passing something into a function, yes. The return value case is really more of an edge case that you should be aware of. That's one case where you should move, but otherwise, if you have an L value, which typically just means if you have a variable that you're not going to need anymore, and you're passing it to something, you might as well move it.
Okay.
Or you should really move it.
That makes sense. So it's a way of tracking ownership as well.
Ownership isn't really the right word for this. It's more of like it tracks sort of, yeah. If you move, you're indicating this resource is moved from here to there, so sort of ownership, yes.
Rust reference.
I was gonna say something because the reason why move works the way it does again is because this is empirical. We've observed. We've also reasoned, because it's something that you just notice. It makes perfect sense that temporaries are reused immediately, right? So we don't need to keep the original value. Because we don't need to keep the original value, we might as well reuse the value. And that's an intrinsic thing about R values. that if they only are used once, they're not used later. Sometimes we want to treat something like an R value, so that it's used for the last time and never after that. And that's what move is for. It converts an L value to an X value. And X value, again, is something that we've told the compiler, this is something we want to reuse now. This is an R value.
That's making
Okay.
sense. That's making sense.
Okay, good. We can go over some code examples later, something if you want to, perhaps. Okay, one last thing, and this kind of ties everything together because you have to understand the rest to understand this. And if this section seems long, that's just because the code examples are longer. It's not actually that long. And it also ties into what we discussed last time, variadic templates. So now that we know how moving works, we can discuss forwarding. As the name would suggest, forwarding is typically used to forward something to another function. And there are various use cases for that. For instance, we have this template here, which basically just is a roundabout way of calling a function. What is this good for? Well, this in and of itself doesn't seem particularly useful, but you can, for instance, do some logging in here or transform some stuff or whatever. There are different applications for these sorts of wrappers. It just happens sometimes that, okay, we have a function, we pass in some arguments, we want to pass those arguments to another function. Okay, syntactically, you can do that with the variadic templates. You create a parameter pack here, and you just unroll. You just unwrap that and expand. That's the actual term. Let's see. You expand this pack here, so this just inserts all the arguments here separated by commas. Okay? Any questions about what this does exactly? Because we discussed that last time already. Okay, I presume not.
I think that makes sense. That's just, yeah, the template packing we went over.
So this just takes f and args and calls it, and we can look at an example here. We have this callee here. It takes two strings and the rect of a reference. We have a string here. We have a bunch of ints, an int vector, and we can call it directly, obviously. That's just a regular function call. We pass in this here. We pass in this string here and the ints here. Or we can pass it to invoke, pass both the callee and the arguments to invoke, and invoke will then basically perform this call here. Okay, and also we assume here we have made s a variable here, so we assume that s is still needed here, otherwise we would have moved it here somewhere. We presume we still want s later than that, so that's the assumption we're making here. Okay, so let's take a look at this code, because there are some problems here. It compiles, but it's not exactly ideal, for many reasons. If we analyze this call once to recapitulate how all of this works, we pass an L value here to this parameter. That means we create a copy, right? This passes by value, and passing by value means creating a copy. That's what happens here. However, in this case, the return string is a PR value. So in this case, copy elision applies. No copy is performed. It's directly used for the parameter B. And what I've written here is this value here isn't copied, but rather conceptually it becomes that copy, quote unquote. It's used directly as the by value parameter of the call. And that's due to copy elision. And finally, this ints vector here is passed by reference. So in total, we have one copy in here, but that copy is necessary because we assume that s is still used later on. For some reason, callee decides to take by value, so this copy is unavoidable. Okay. That's this line. There's nothing unusual about this, but there's some problems here. And the fact is we have two calls to look at here. This initial call to invoke, and then this call here that gets generated. We need to look at both. Let's look at this one. Here this is just the function. That just is a function pointer that we pass by value. That's not particularly interesting. We pass s by value again, because in here we've declared a pack of arguments and we haven't specified any references in here, so this just passes by value. We pass s by value. Return string. Return string is again a PR value, so that just gets passed in, no copy. But the first difference is here. This takes by value. So what this does is this actually creates a copy of ints. It's passed by value, so we create a copy. So already we see we already have one copy more than in this case. Okay. Now let's take a look at what gets instantiated here. So the instantiation for invoke here ends up looking like this. That's the function that gets generated. First, we have this function pointer here. This is just the type of callee. Since we passed by value, all of these parameters are taken by value. And we just discussed that. However, let's take a look at this call here, and this is where it gets dire. This is where it gets really bad. It's important to know that template argument deduction won't deduce a reference unless you tell it to. Meaning if you write argb, where arg is a template parameter, it's basically as though you'd written string b. If you want to pass a reference, you'd have to write arg reference b. The same applies to packs. So here, both arg1 and arg2, their L values, both of these are now passed by copy, this function. And what is worse, this vector here is a copy of this one because we passed by copy. So although we pass it by reference to f, which is just callee, if this function ends up mutating this vector, then the original vector never gets changed because we pass in a copy. So not only is this code inefficient because we suddenly have 1, 2, 3 copies instead of 1 earlier, it also doesn't do the right thing. It just mutates a completely different vector. So this code is just wrong. It doesn't actually do the right thing. Okay, so how do we fix this? Well, solution, there are several attempts. We could try and move everything in here. Just move arg1, arg2. That gets rid of these 2 copies. It doesn't get rid of this copy here. It also passes the wrong vector still. So that doesn't help. Moving is not a solution. You could pass everything by L value reference. I would get rid of the copies. I would pass the right vector. But we remember what we mentioned earlier. We can't bind L value references to R values. So we couldn't pass in temporaries. We'd again have to do the horrible thing where we create a temporary variable, pass that in. So that's better, but that's not really a solution either. So we could pass everything by R value reference instead. Both of these are L values, and we kind of need them to be L values here. And furthermore, we want to reuse string later, so we can't just move it. This always has to be an L value, so we can't make everything an R value reference either. We could pass everything by const reference, but that doesn't help either because we'd still get the copies here. And also, f needs to mutate. It needs to accept a regular reference, not a const reference, so that wouldn't work for this either. So no matter what we try, if we try to pass everything the same way, no matter what we do, it just doesn't work. So, what you do, a universal argument passing scheme doesn't work. You need to do something else. So, in order to figure out what to do, let's construct what an ideal instantiation of this would look like, what we would want this template to instantiate to. And ideally, we'd want it to look like something like this. The first string, which is our S, is passed in by reference, which we don't copy here. Second string is an R value, so we bind an R value reference to it. That eliminates the copy. Then we move it in here. That eliminates this copy. And then we pass this by L value. Yeah, I missed the comma here. Yeah. Pretend there is a comma here. Thank you, local. So yeah, and this, since we need to pass it, oh, this is an error. This is, okay, I'm going to fix that because that is very wrong. This needs to take an L value reference, not a const L value reference, okay. Hold on, I'm going to add the comma as well if I'm already added and make sure that didn't get that wrong. I did get that wrong everywhere else because I just copied this damn function. That's why you don't copy code. That's why you don't copy code, okay, I'm almost done. Just so we don't get confused. Okay, it should be fine. This is probably gonna jump forward now. We don't want that. Let's go back up. Yeah, this is our ideal instantiation that we're conjuring up here, basically. So again, this is an L value reference, so we pass it by this is an S is an L value here, so we pass it by L value reference. This is an R value, so we bind an R value reference to it. And this is an L value reference, an L value. We need to pass it as an L value reference, so we bind an L value reference to it and just pass it along. This code does exactly what we want it to do. It still requires one move, as opposed to the original code here. If we call callee directly, that requires just one copy and no move. But that's pretty good. That's not too bad. One copy and one move versus one copy. That's okay. So, how do we actually get it to stamp out this instantiation, though? Because the problem is, if we write something like args ... args, all of these args are passed by value. If we write args ref ... args, all of them are passed by reference. So we can only pass them all the same way. And also the thing is, the fact that the first parameter should be passed by L value reference, the second by R value reference, and the third by L value reference as well, that's just specific to this one function. If we're calling this particular function here, for other functions we might have to do something different. So we sort of need a different approach to this altogether. We need a general way to, and this is where forwarding comes in, a general way to preserve the value categories of what is passed in. Ideally, if we get passed in an L value, we want an L value. If we get passed an R value, we want an R value, and so on. We want to preserve the value categories of the values we're passed in and forward them to the callee. So how do we do this? There's two parts to forwarding. That was also added in C++11. Like C++11 added pretty much all of this. The first part to forwarding is a forwarding reference, which is sometimes also called the universal reference, but I'm pretty sure the official term is typically forwarding reference. Forwarding references can bind to anything, be it L values or R values, and they preserve the value category of what they bind to, meaning if we pass an R value, the forwarding reference will be an R value reference. If we pass an L value, the forwarding reference will be an L value reference. And because of that, forwarding references only make sense in templates. Outside of templates, they don't really make much sense because of this. In templates where the type of the parameter is deduced. The problem is, that's one of the things that can get annoying in C++. It doesn't like using or introducing new operators or keywords. So what they decided is they just reused the add syntax, the ampersand syntax for forwarding references as well. Which means that R value references and forward references use the same syntax. Okay, if they use the same syntax, how do we know which one it is? Okay, so the way we know which one it is, and this is how it's defined, is T ref is a forwarding reference if and only if T is a template parameter. Otherwise, it's an R value reference. So if we take a look at this, for instance, we have another template, foo, takes in a type and also pack. This is an R value reference because this is not a template parameter. This is still an R value reference because this is not a template parameter either. There's a template parameter in here. The entire thing itself is not a template parameter. However, type is a template parameter. This is a forwarding reference. Args is also a template parameter, so this is also a forwarding reference, or rather a pack of forwarding references. Okay, so this is something to be aware of. Unfortunately, they use the same syntax, so the only way to knowing which one it is to look what's to the left of it. If what's to the left of it is a template parameter, and that's all it is, it's a forwarding reference.
AST nodes go burr.
Yeah, if it merely contains an R value reference, that doesn't mean the entire thing is if it merely contains a template parameter, the entire thing itself is still not a template parameter. That's still an R value reference. Okay. So, armed with this knowledge, as I wrote here, we can rewrite our template from earlier to use forwarding references. And as a side note, we could forward the function itself too, but for simplicity, we're not doing that here. So instead, same thing as before, except that we write args ref here, which is a forwarding reference because args is a template parameter. Okay. So we had this call here from earlier, and now the instantiation looks like this. function is passed in unchanged. This here, this argument, which is s here, is an L value reference because s is an L value. The forwarding reference is an L value reference if it's passed an L value. This here is an R value reference because return string is an R value. This is an L value reference because ints is an L value. So passing by forwarding reference mean we always pass by reference. Depending on whether the thing is an L value or R value, it ends up being an L value reference or an R value reference. So, you'll notice this is already looking a lot closer to this ideal sampler instantiation that we described earlier. At least the parameters are looking correct now. So now arg1 is only copied once in here. arg3 isn't copied at all. So this code is actually correct now. It does the right thing. It's not just not inefficient, it does the right thing. The only little thing is arg2 is still copied here, because recall the thing we discussed earlier. A variable of R value reference type is still an L value. So this is still an L value, so it still gets copied when it's passed to this parameter. So if we've reduced the number of copies from, what was it, 4 to just 2, and the semantics of our code are correct, it's still not quite as efficient as it could be. Ideally, we'd want to move this. What we could try to do, we could try writing move in here. We can do that, we just wrap all the arguments with move. What this amounts to is this. It ends up looking like this, we move all the 3. However, immediately we can see something is wrong. Now moving arg1. Recall that arg1 was our s here. We have established up here that s is still used afterwards. That's why we are passing it in by value, as an L value. In fact, the only reason why this is an L value reference is because we passed in an L value. If we had wanted to move it, sorry, here, same thing, but here, if we had wanted to move it, we would have moved it, and it would have been an X value, which is an R value, so this would have ended up being an R value reference. The fact that this is an L value reference means we don't want to move it. Now all of a sudden we're moving it. Like, this code suddenly is not correct anymore. Sure, the copy is gone, but the code is wrong. Because S is just destroyed here, basically. S is moved from, and then we try to use it. So, yeah, if we had wanted to move it, we would have put the move here. We can't just hallucinate a move into existence here that the user didn't want. So obviously this approach doesn't work. Clearly, it's not as simple as just wrapping the entire thing in move. We only want to move some of the parameters, not all of them. Particularly, we only want to move R value reference parameters, but not L value reference parameters. So how can we accomplish that? Well, what we could do is, for any one parameter that is declared with a forwarding reference, if that forwarding reference ends up being an R value reference, then that means the value passed to it, the value it's bound to, was an R value, which is either a PR value that we can just move, or an X value that the user told us to move with standard move. So, in other words, we want to move a parameter if its type is an R value reference, but not if it's an L value reference. And we can use a trick for that. What if we cast each parameter to the type it was declared with? It does sound pretty stupid, admittedly, at first. We're just casting to the same type. Really. For L value references, that is true. Just casting L value references to L value references. But that's not true for R value references. Because in a variable of R value reference type is an L value. We've established that the variable itself is an L value. But its type, the type it was declared with, is still an R value reference type. So if we cast it to that type, we end up leaving L value parameters as they are, but parameters of R value reference type are cast to R value references. And we can use the decal type operator for that, which retrieves the type that a variable was declared with and not like the actual value category that it ends up being in an expression. So if we put the static cast in here, we pass to the decal type of args, then our instantiation looks like this. We suddenly have these static casts in here. We cast arg1 to decal type arg1, arg2 to decal type arg2, and so on. And if we insert what decal type evaluates to here, we get this. arg1 is cast to an L-value reference, arg3 is cast to an L-value reference. Both are already L-value references, so these two casts are just no-ops. They don't help, but they don't harm us either. We can just leave them. The interesting case is this here. This should look familiar. This is a cast to an R-value reference. And we mentioned earlier, a cast to an R-value reference is a move. That's how move is implemented. So, what casting to the decal type of args actually ends up doing is, if it's an L value, it's just passed along. If it's an R value, it gets cast to an R value reference and thus moved. This cast does exactly what we want. This cast ends up being the same as standard move of arg2. In other words, by casting each parameter to the type it's declared as, not to the value category that the variable is, but the type that it's declared as, we end up moving R values while leaving L values unchanged. And as with moving in standard move, standard C++11 also added a library function to simplify this, so we don't have to write this horrible cast ourselves. That function is standard forward, and also it exists so we can have at least a chance at teaching forwarding without explaining all of this. So we can use standard forward here, passing it the decal type of args, and it then just does the right thing. It performs this cast.
Funky.
And also, alternatively, instead of using decal type, we can just pass args directly to standard forward. Standard forward is clever enough to figure out what to do with it. Note there's one thing to keep in mind here. If we try to just static cast to args up here, that wouldn't work because of some technicality that I'm not going to go into, but if you're doing the cast manually, you have to use decal type. Forward is clever enough to figure out what it's actually supposed to be if you just pass in the parameter. So for standard forward, you can also just pass in the pack, and that's how we typically do it, because writing this is a bit painful. Now, there's a few things to note about how to use standard forward, because it's easy to get wrong if you don't know what it does. So it's very important that you write standard forward args of args ... and that you don't try to expand the pack in here, because we don't want to pass all of the arguments to one call to standard forward. We want to forward each argument individually. So we have to expand this entire expression over both packs. So put the ... outside. And now you also know why standard forward of just args without any template parameters is nonsense. We need to tell it what it's supposed to cast to. We can only get that information by looking at the type it was declared with. If we just pass in the values, well, they're all L values because they're all variables, so they'd all be deduced as L values, and standard forward would be useless if we just passed in just the arguments. So this is just basically straight up an error. It compiles, but it definitely doesn't do what you want to do. Instead, you always have to pass in the arguments here, and that's why this may seem a bit weird at first, because you're basically telling it what it is twice. You're not. These two are different things. This is the actual type, and these are just L values. We need to tell it what the type is supposed to be, either by using the pack or by using decal type. You can also use decal type, but if you have the parameter, just use that because it's typically shorter. So yeah. Now you know how standard forward works. And Lens, I see we've got a Raiden on Twitch.
Ooh, Zorkenheimer, thank you so much. What's up? Hello, everybody. We're just nearing the end of a C++ value types talk by Eternal, one of our valued community members.
Yes. We're just talking about standard forward and how it works. Okay, yeah, again, if you just call standard forward without this pack, it would only ever return L value references, which would defeat the entire purpose of having forward. So that's why you need to pass in the pack too. Some last little notes. These are just, you understand how standard forward works now. If this is the main thing. It wasn't really that complicated, was it? Standard forward in and of itself isn't complicated. All the other stuff is.
Right. What makes it work is complicated.
Right. What makes it work is complicated, and what it enables. Some last notes. Those are just the last page, and then we'll be done with this. We've previously said that for a ref reference to be a forwarding reference, it must be a note. Has to use 2 ampersands, and it must be such a reference to a template parameter. That's correct, but it's a bit imprecise. One more thing is the template parameter must be a parameter of the template argument list of the function itself. For instance, it's common to have a template struct that contains a template. In this case, urefref is a forwarding reference because u is a template parameter of this function. Trefref is an r-value reference because even though it is a template parameter, it's not part of the template argument list of this function. Okay? So that's something to keep in mind, particularly for things like constructors, because people get that wrong sometimes. Just because the template parameter doesn't mean it's automatically a forwarding reference. That's only the case if it's template parameter of that same function. Okay? Just one thing to be aware of. This situation doesn't come up often, but when it does, just be aware of that. Okay. And one last thing, this is slightly more modern, because all of this basically is mostly C++ 11. All of this actually is just C++ 11. We've just been talking about C++ 11 for an hour. That's how important C++ 11 is. Okay, that's the start of modern C++ with all of this. C++ 20, slightly more up to date, introduced abbreviated function templates, and that syntax was already there for lambdas since C++ 14. So you can now just write this, and this is equivalent to just this. So you can, if you write auto here, that's just a template parameter. And I'm almost done explaining this, so then we're going to address some questions in chat. Because this is equivalent to this, since we could forward in here, why not allow forwarding in here? And that's exactly what we can do. So auto-ref is also a forwarding reference. That's a special case. Auto-ref is one way of writing forwarding reference. And in this case, there is no template parameter type. So in this case, we have to use decal type. So if you're using auto-ref, you have to use decal type. That's the only way of getting it because there is no key parameter here that we could pass in. And that's pretty much the last case I wanted to mention. So if you see this code, this is the one example where I use decal type to forward instead of something else. Okay. That basically concludes this.
Woo!
We've talked, yeah. If you have questions, which you might very well have, I'm happy to answer them now. And to go, if you want me to go into more detail to some things, I can, but I've left out the technicalities that are really not that important to realize. Like the most important thing about all of this is to understand motivations behind why these things exist. And if you understand that, you also know how to use them and when to use them. And hopefully you'll remember that once the time comes when you're in a situation where you need to use them.
I sure hope so. I don't know if I have that much confidence in my ability, but I do know that this video will exist for a long time, and I'll probably watch it a lot.
This is a lot to take in. Obviously, if you can't remember all of this immediately, that's perfectly fine. It is a lot to take in. It's enough if you remember the important parts, such as standard move doesn't move, the surrounding code does. R-value references can only bind to R values, and they are what enables moving, and so on. And forwarding is used to make sure we pass everything along correctly.
Nice,
and all of that. So now if you see this code, even if you don't know how to write it exactly off the top of your head, you might have to look that up. That's perfectly fine. Like, you might not exactly remember what exactly to pass into forward. You can just look that up. But now you know more or less what's going on there. So it shouldn't just be some confusing thing that's just there and exists. It actually has a reason why it exists, and now you know the reason.
Yeah. It'll definitely help an immense amount. If I didn't have this, I'd have nothing. Local has to go. He might miss the end of the stream, so everyone say goodbye to Local. Thank him for being here. He's super awesome.
Goodbye. This was good talk.
Thanks.
While you were giving that delicious, juicy talk, I was able to do a couple of things in C++, believe it or not.
Right now?
Yeah. So let's take a look at... Here, I'm going to go switch the stream over.
Take a look at that. I can stop sharing my screen for now, I suppose. If there are any more questions about this, I'll just feel free to ask in chat or somewhere, and I'll try my best to answer them.
Fantastic.
And I almost pressed the disconnect button again.
Oh god.
Or to press stop streaming. I keep doing that every time. Okay, I'm gonna switch over to full screen now.
Awesome. Okay, so I want you to tell me if I did a bad.
Oh, just real quick, on Discord, Pyro Death Adder is asking, will the notes be available? I'm gonna put them up on like GitHub or something, and you can put them in the not the LaTeX sources probably, because those currently work with an extremely cursed variation of my package that I threw together in like 2 minutes, which is horrible code that I don't want to put up candidly. I'll have to refactor that, but I can put up the PDF for certain, yeah. And then Lens, you can put that in the description or something.
Yeah, and then it'll also be in the Discord if you join in the resources section. We'll upload it there.
Oh yeah, I can definitely upload that there, so I can do that real quick. That's
Beautiful.
not a problem at all.
Also, just another shout out to Zorchenheimer. Thank you so much for the raid. I appreciate it. Hopefully everyone is enjoying. And oh, did you the question in chat? Did we get to it?
Oh, what question? Oh,
Who are
I thought
you?
I saw one. I'm not sure anymore.
Meatball1 asked, what is the name of the speaker and where/how did they learn this in such detail?
The way I learned is because I've been programming C++ for a while now, and not just that, I also watch a lot of conference talks and read proposals and stuff like that. And if I don't know something works, I tend to look it up in a standard or a CP reference. And if you program in C++ for long enough and you're actually interested in learning about it, you'll pick up these things eventually.
Yeah. Okay, so I wrote some IR types. Here's the array type. Did I do a big bad?
I'm uploading the thing real quick. It's now on, if you want to take a look at it, it's on Discord, and we can link to it later. Okay, so let me take a look at what you did.
Okay, here it is.
Because someone mentioned, oh, Meatball1 is mentioning a bunch of C++ people. Yeah, all of them. My favorite speakers are probably Andrei Alexandrescu, obviously, and Herb Sutter.
I like Herb
Andrei
Sutter.
Alexandrescu because he's just very funny, and Herb Sutter because I like his talks about the future in C++ and everything. He is I would say, understands C++ very well, and also has a very good grasp on where it should go and everything, and also because he's kind of the chair of the committee, sort of, and he's been programming C++ for decades, so he knows all that very well. Anyway. So, array type, you said. This, I think, at first glance, it looks right. It has a length, an element type. The kind is array. That's good. Class of returns array. String returns a string by value. That's not... oh, actually, no, that is fine, because... No, actually, that is not fine. Array type should not have that. Just type should have that. And type will then switch on what the kind actually is. If you wanted to do it just
okay.
virtual, which we don't want. So...
I see. Okay.
Yes.
I figured it would work on some sort of overloading, but that makes sense. So it's just on the
Nope.
base type. We don't need one for
Overloading
each one.
on the dynamic type is exactly what virtual functions are.
Oh, fantastic. Okay, that was the only string one. I'll get rid of that.
The rest of that looks right, though, I'd say. Yeah, sure.
Phantasmo.
Struct types, yeah, I think struct types in the IR, do they need a name? We could give them a name.
What did I remove this from? I didn't remove that. No, okay. That's array and struct.
What's that diff thing someone's asking? I'm presumably talking about this screen here.
What is that diff thing? So this thing on the left and right is a feature of an Emacs package called Magit or Magit. M-A-G-I-T, like magic, but Git. And it's a transient key map system that has temporary window pop-ups for all the Git commands that you run. So right now I'm doing a Git commit and I'm writing my message on the right, and here's the diff of the commit on the left. And I can select specific portions of this particular gray box is called a hunk. And then you can select particular lines in the hunk and stage or unstage those for commits. I really like Maggot as a Git porcelain.
It's basically a GUI for Git, but in Emacs.
Yeah,
Sort of, at least.
because like when you run git commit, it already opens Emacs.
For
If you have it
does,
as your
yeah.
text editor, yeah. So it's like it's close enough for me to the
I
command
have
line.
my text editor actually set to Vim simply because I don't really use Vim much, but in the terminal it opens faster than Emacs because you can run Emacs in the terminal, but it's annoying. It's a bit cursed Emacs in the terminal.
Yeah, it's not what it's meant for anymore, really.
Yep.
Unless you're doing like a bare bones, just need a quick editor. Oh, I haven't fetched. What have I done?
typically use Vim or VI because that's simply already on every distro.
Remember when you're
It's fine for small edits.
That's right. Remember when you're fetching and merging to do the -R to rebase local commits, which means that you don't need to do a merge commit after you pull.
I don't do merge commits, I just rebase.
Exactly.
It's called git rebase manually typically.
Oh, I can't change. Why did?
Yeah, yeah. Unstaged changes you can't rebase. Well, you have unstaged changes. You have to commit first, either commit first and then rebase, or stash all.
Untracked is
Oh,
fine,
okay.
right?
Untracked should be fine, but not unstaged.
Yeah.
For sure.
I don't think I need any of this. I was just testing out what context was because I think we're going to use context and add all the input
Context.
files into that.
Yes, yes, very good.
Fantastic. Okay, so we'll just commit that then.
Also, I see you already did something interesting in there.
So-
It's not ideal because you're copying the vector for no reason.
I'm copying the vector for no reason.
Yeah, if you look on, I'm not sure if you did that or somewhere else, but if on the line get input files, there's you're dereferencing that, and that's a pointer to a vector, so that ends up copying the entire vector. What whoever wrote this should have done instead is just declare input files as a pointer to a vector and just keep the pointer around.
Why wouldn't we just? I mean, we're going to be iterating over strings.
Yes,
So we're just going to dereference
does-
it here.
that dereference is there, but that doesn't create a copy.
It
Because
doesn't.
just dereferencing doesn't copy. It just creates an L value reference, basically.
So I should do auto.
Auto would work, yes. That's a good idea. Always do auto. Auto or auto pointer, that works, yes. Because
I'm
since
just
we
gonna
just talked
change
about
that
value
to-
categories, this is an interesting case. Let's talk about this for just a bit. It won't take long if you can bring it up again.
Yeah.
We have on line 39 here. A dereference, at least conceptually, creates an L value reference. And then in this declaration in here, since the right-hand side has to be a PR value, we apply L value to R value conversion, which creates a copy. That copy is a PR value. That PR value is then becomes the object input files. That's what happens here. In the range-based for loop, if we dereference in there, that's another way of doing it. The difference here, also, you can just use options, not detail colon options, because I'm short. Anyway, the difference here is that this only creates an L value reference, but then the code that implements the range-based for loop, it doesn't copy, it just uses the reference and grabs begin and end and stuff like that. That's the difference here, basically.
That makes a lot of sense. So yeah.
Now I can explain how the difference works.
Okay, so we're gonna build this. This should still work. Funky.
Compiles, actually? I'm surprised, honestly. Library compiles now? Did you stub out some things? Oh, probably because they're never called. Ah, that makes sense. That makes sense. Also, this is a... what are you using for file name? What does your options type look like? Can I take a look at that real quick? Aluminium is there.
It's the most important one.
You figured out how to use func. Well done. You have multiple positional, that's good. You can actually use multiple positional of file, and then we'll load the file data automatically, and then you can just add that to the context if you set the option type to file.
Here?
No, that's after the description. It's file, and you have to put like an empty template argument list. After the description, that's the name.
Saying in
Inside of
here.
conditional. Yeah, the option type goes here, yes. So just file and then opening angle bracket closing out. Yeah, there you go. Because you can't, that's another annoying thing, you can't pass in a template in this situation without specifying any parameters, so to tell it to just use the default to that. And then in here, instead of strings, you now get files, and those have a file path and the content. It already loads the content. I don't know if it's called file path, I'd have to check, but
Well, you said it, not me.
I don't know if it's called file path, it could just be called path, I don't know.
By the way, it says downloading format lib every time. Is it downloading format lib every
That's
time?
CMake thing. No, I don't think it is. It's just checking the Git. It's just doing a Git pull, basically. I think it's awesome.
Oh yeah, this thing is no longer.
It's no longer
printable.
formattable. And file path is a path that's not formattable either. You have to call .string on that.
Of course.
Same thing on line 57.
Ugh.
I'm not sure you can call ends with on. Oh, you're calling it. Okay, yeah, sure. That works. Because this way it loads the contents in the fastest way that I know how to do it on whatever platform you're on.
Map. Meatball One says Vim is a more than decent editor if you take the time to learn it. Sure.
Sure, I don't. That's the thing.
Why is it mad?
Probably because it's not called file name or file path.
Well, why would you
check what
call
it's
it
called.
something crazy?
I don't know what it's called. I haven't used this feature in a while.
What's
I
wrong?
rarely use that.
You're insane. Where's the actual source
It
code for
should
this
be
stuff?
in
There it
depth.
It's
There
in
you go.
libs,
It's
libs.
in include. Yeah. We go. Just search for, I think, class file or struct file or whatever it is. File data. That's what it's called. Yeah. I think it's called path. There you go.
Path and contents.
Path and contents. Yes. So it's close to file path, but it's just path. Because obviously there has to be a file, so that's probably why I call it path and file path. And also in the conditions of the if statements, yes.
I'm starting to understand now.
Mm-hmm. You have to rename the variable itself to input file too, if that's what you're doing, or input file. Oh yeah, input file. That does make more of a sense. That name, yeah. Yeah, there you go. Let's see if that works. You can also see your LSP seems royally confused by some part of the options type.
It's confused from the get-go, yeah.
Interesting. It's
Too
just
many
confused.
errors omitted, stopping now.
That's it. See, that's a funny one. Look at that error. Invalid. I think your ClangD version is too old to understand GNU++ 23.
That's likely. Yeah, it doesn't understand concepts. Still not formattable.
Did you forget to put... Yeah, on line 49 you have to also call string. That's the annoying thing about paths being wide chars on Windows. And path doesn't have ends with either, so we have to call string on that as well. Brilliant,
Oh,
isn't
for
it?
fuck's sake. That's why I like Emacs. I just did all of them at once.
That's what I also do in CLine typically.
Hey.
Hey, now it errors if you can't load the file, by the way. That's the options library, it just does that.
Which is really good. I was going to have to write that.
Yeah, now you don't have to. This is why it's in the library, see? Just so you don't have to rewrite. That's the main reason I wrote this library to begin with, so I don't have to reinvent command and options passing every time, because it's just annoying.
Yeah.
There's really much to it. There you go.
We're doing it. What's our API going to be? How's this going to work?
How's this gonna work? So basically, you're just gonna create file. You need to register the files with the context, basically.
Yes, but
there is
like,
some
how
way
are
of
we
doing
actually
that.
going to do the front-end interaction?
The front-end interaction, we're gonna create a parser, or rather, we're not even gonna create a parser. We're just gonna call the parse function, which takes in file, I think. I'm not sure if that API exists yet. I think for intercept,
doesn't.
for intercept, it would be. LCC : intercept : parser : parse, or something like that. A lot of colons. Namespaces should be lowercase.
Like this.
And I'm not sure if parse is static, so it's probably capitalized. You can check the header for that. Should be. That should take in, I think, a reference to a file or something like that. We'll see. It takes a context and a file, yeah. And the context you already have, you can just pass a pointer. The file you get from the context. You need to tell the context what the file is, because the context has all the files. So, and there is context.
Isn't that going to make it so we need strings again?
Sorry, what?
That's going to make it so we need strings again.
Oh, you can just pass in the file. You can create the file. I think you can call create file for that.
What does this do?
That should take in a path and a string, if I'm not wrong. If it doesn't, I can change it to do that. It takes a buffer, which can be anything. Yeah, it just casts it to a vector of char. So yeah. Why does it use it uses a vector of char, so you could okay, I think whenever this is copied probably from an old project, and because standard string doesn't like binary, so if we need to register binary files, we can do it with that. But if we don't need that, we can also change that. And for the contents, what you can do is you can also specify to load it as a vector of char. You can put like standard vector of char in the file thingy as the template parameter in the options type. That way it will load the contents as a vector instead of as a string. Because I need that sometimes.
Like this?
That should work. Yeah, that should work.
Ridiculous.
If it doesn't, then
Okay.
it's my library. Mm-hmm. LCC intercept, you probably need to include the header for that. It should be intercept parse. It's not LCC intercept, it's just intercept, because we decided to put that at the top level as well. Otherwise, you'd have to write LCC in front of everything.
No, it didn't work.
Let's see why it didn't function. Oh, you
But
forgot to
there's no
pass in the
error
context of the
message.
file.
Jesus.
You pass in the context in the file.
Why is there no error message?
That's where the error is. The error message is below that. It says, where's the, hold on, let's see, where is the actual error message?
It says arse or parse.
It lists all the, that's interesting, it just lists all the it doesn't even say overload resolution failed, it just lists the candidates and expects you to know what happened here.
It's really annoying.
GCC brilliant.
You said it's something to do with the arguments?
Maybe it's a terminal cutting off a line again, I don't know.
What are you talking about?
Your terminal, you told me, tends to cut off the top line. Maybe
that could be it.
The error message, I don't know. So the way this is supposed to work is you create a file and that returns a reference to the file. You can then pass that into parse. You can just, yeah, it takes a. You need to write auto ref because auto never deduces a reference unless you write. Yeah, there you go. So someone's mentioning Herbset as CPP front or CPP2. Yeah, that's a very interesting project.
Very exciting. Oh, it was the terminal cutting off.
It was. There we go. It's not GCC this time. Did you also pass in the context?
Yeah.
Okay. Did you pass in the context as a pointer or as a reference? Because we're passing the context by pointer most of the time because you need to store it, and storing a reference is a bit little janky. So, and most of the time it's already a pointer, so that's easier. Okay.
Meatball 1. So you're doing extreme programming now, apparently.
You forgot a semicolon.
This is why intercept doesn't require semicolons. Jesus.
So, and that function call returns a module, a unique pointer to a module that you can then pass to. Obviously, they get a bunch of undefined reference errors because now you're actually trying to call all of these functions that aren't really implemented yet, apparently.
So the
Just
intercept,
macro expansion.
next macro, next char.
Yeah, because obviously
This
it's not
Alexa.
done yet. You can't really call it yet. It's not done yet.
Local, you're too slow. I know you're not here, but you're too slow.
Yeah, I'm done with the parser, so I'm going to finish the the macro system in Alexa, and then we'll actually be able to use it. But until then, just get liquid errors. Yeah. So the way to answer your question of how you're supposed to use this afterwards, this function returns a unique pointer to a module. You can then run Semma on that and like call a codegen function or whatever. None of that is implemented yet because neither Semma nor codegen, but like you'd probably just call module dot, or in this case arrow emit, or emit as object, emit executable, and whatever.
So we're gonna do like something like this.
Yes, I think it has to be LCC : intercept : module, because it's an intercept. Actually, this is a front-end module, so this needs to be Semma, and then codegen will turn this into an IR module that you can then code. Yeah, the entire thing is a bit more complicated now, simply because we also have another front-end now. So
Yeah.
that's how you invoke the parser, and the rest isn't really implemented yet. So, but like Semma should work differently, either by just calling some static function that takes a module, or by calling some member function on a module. Yeah, so this does no Semma. Other than like very basic stuff, such as if you declare variables with the same name and the same scope, that it will error on. Right, I'll be right back.
Okay, I'm gonna start wrapping up the stream, but it'll be like 5-10 minutes.
This is sure. I won't take that long.
Fantastic. The extreme programming comment was that you are two and you are coding together. I see, yeah. There's 3 of us actually. We're all just pushing to the same branch. It's fantastic. See? Wait, is this what I think it is? Asks Dwyer. Dwyer is here. Fantastic. By the way, this stream has been a little different, but let me just shout these out. Zen Mystic, Computer, NetCorp, Jukara, Dens, Cold Mayo Plays, Vapesco, Amos, I Am Yeezy, Swax, NG Dev, Zod101, Battyland, Louisa Forsey. I can't even comprehend how many there are. And Henrilly, Blemgang, Barkeith, thank you, Nautic someone, thank you so much for the follows. I appreciate it so much. And Swaxy, thank you so much for the follow. I really appreciate everyone joining. Can't believe we're at 819. That's absolutely bonkers. That's more than my mind can comprehend. Ooh, we just passed the 3-hour mark. How fantastic. We've been talking about C++ for 3 hours. Okay, I was doing the context stuff. So now we do the context stuff. MetaMe, thank you so much for the follow. I appreciate it. Okay. So we're going to begin the reckoning. I swear I thought I hit the button before. I missed the stream. Oh no, Zen Mystic. You know, if you're missing streams, if you join the Discord, there's the announcements channel where I announce every time I go live and at the notifications group. So if you join the Discord and ask, hey, give me notifs, I'll give you notifs and you'll be notified every time I go live. That should ding your phone if you set it up to do so. So yeah. And you can be a part of these awesome streams yourself. You can join. Oh, is Dwyer here? Dwyer's here. And so is Jemus. Fantastic. We are doing well. Okay, we're going to commit into some of this stuff. What do we want? What do we want? Oops, I got to open up this chat again. Otherwise, I will forget it exists. Okay. Do-do-do-do-do. So we need to poll. So we're going to poll, and then we're going to rebase our local commits, which means our local commits here that we've already made. Oh, I can't do this yet. God, I
Did
have
somebody
to
say
make
local?
the commit. I did, but in reference to commits. How are you doing? It's good to see you.
I walked to the store and I came back with some candy.
Hey, what a legend.
So I am doing just fine. I'm gonna eat. Have you ever had a Zero bar?
No.
Fucking good.
Hey.
Top 3 candy bar for sure.
I'll have to try it if I see it. Okay, now we should be able to pull. And now that we have no unstaged or staged changes, our work tree and our index are completely clean. We should be able to rebase our local commits during this poll, which should put our local ones we've made that are unmerged after the poll, the ones that we poll, so we can still make these commits and will not require a merge commit.
Woot.
And there we are. Local, we've began driving.
Hey, yo.
We now have the actual line that will parse intercept files. If we do
Missing
it,
that auto keyword.
yeah, you know what the issue is?
What?
You know what we ran into if we try and parse?
Uh-oh.
Dun, dun. Dun, dun.
What did I do?
You didn't do.
What the heck?
No, it's
How
just
did I never
next.
actually call?
Ah, too loud. Down by my volume.
It's just next
I was
char is not defined, and neither is next macro, obviously. But I think
Next
Eterno's
char
going
is
to do
probably
that.
defined. It's just some. Is next char not defined? That would be interesting.
It says it's undefined.
Oh,
Interesting. I could have sworn
I
next
guess
char.
we got to implement next char. I mean, that's not too big of a problem.
Yeah, should be easy.
Yeah, next macro I expected. Like I said, I didn't finish the macros, but
Yeah. And then in the parser, there's one, I think, too.
So because in chat someone is asking, are we making a C++ compiler? No, we're making a compiler in C++. Yeah,
That's right.
making a C++ compiler would be a bit more complicated.
The only reason we're
here.
not going to do that is because parsing C++ is
Like the entire front end for C++ is complicated. Yeah.
yeah, the type checking isn't going to be good either, but it's not as bad.
Parsing and saying you kind of do that. You have to do that at the same time in C++ for that to work. So it's complicated. Yeah.
How many languages does this compiler support, actually?
2 at the moment, but you can add one if you want.
Nice.
You can have
Wow.
more than one if you want.
It also supports the IR, though, right?
Yeah.
So I guess 3.
And then technically there's a language, a DSL in the compiler
Yeah.
used for instruction selection. So there's 4, but it's not really one.
Mm-hmm.
Making our own GCC, basically.
That's right. So may start an expression is not implemented in the parser.
Yeah, I forgot about that. I need to implement that. Oh yeah, and another note about that, because we discussed that briefly. I've since remembered why the semicolon after return doesn't really work. Because the thing is, you can still write something like this. Hold on. I mentioned that this was the problem. That you can conceive of that as a problem, sure. Like this.
So this is what we're talking about. We require a semicolon after a return that has.
Used to, yes.
Well, you're right. This is how
There's a
intercept
Yes. That's
used
how
to
we were
work.
doing it. And the problem is if we take a look at the example that I put here in like
The Discord.
Discord, very simple one. You can just copy that or something. It's literally just if foo return and about. There we go. The problem is with the old system, this would have errored because of a missing semicolon. However, put a semicolon after bar. That would have compiled, and it would still be wrong. So even the semicolon is not really a solution because we don't require the semicolons either. So this would still break. So in conclusion, there's no real good way of doing that. So instead of requiring the semicolon, which is jank a bit because we're only requiring it in that position and nowhere else, what we're going to do instead is we just say if the token after return could be the start of an expression, then we pass an expression, otherwise we don't. In this case, we would pass an expression.
So
Don't want to do that, you
basically,
can still put a semicolon after return. or
if we're
something like that.
parsing a function that returns a value, non-void, right?
We don't know that in the parser.
So
Only
how are
know
we
that it's
doing
SAML.
this?
We look at the token after return. If it could start an expression, we pass an expression, otherwise we don't.
So if it's a semicolon, that will still work.
Yeah, because a semicolon can't start an expression. The same thing goes for a closing brace or something like that.
So, okay, so if we're at the end of a block now, then
Yeah.
we can just type return and we don't need a semicolon.
Precisely.
That's fantastic. But we can
That's the
still
main
use it
difference between the two.
for this differentiation.
And also, if you have else, for instance, else can't start an expression. So,
Interesting. So you don't need it there.
correct.
Even my typesetter, tree sitter, I can never get
Resetter
that
doesn't
right.
even recognize return. So, but I've updated the grammar, so you can now use the updated grammar, which contains a simplified description of how types work to implement the tree sitter thing.
Yeah, that's going to be
Because if we take a look at the
actually
grammar,
fantastic.
we look at the types in particular. This is technically from a this is syntactically correct but semantically wrong because it doesn't take types have precedence now. So this doesn't take precedence into account. However, it destructures types in a way that are easy to parse syntactically. That's not how we parse them in the parser because it's semantically wrong. But you can use this for syntaxality, this grammar. It still gives a syntactic overview of how it works.
Yeah.
So,
That makes sense. Alrighty. Meatball1 says, please PM your address. I will send you a microphone. You should not be using 2 pieces of aluminum foil separated by a thin layer of olive oil as your microphone. Does it sound bad? Why would nobody tell me till
mic
now?
sounds fine, I'd say.
Okay.
Everybody
I've heard a lot worse.
It's a one guy moment. Meatball1 is the first one guy on this channel. Okay. So the C version is all done. That is how I found and joined. I know C, but not C++. Zen Mystic says, no, sounds okay to me. It really was a one guy moment. Oh my God. Oh my God.
Maybe it was somebody else in the chat that's not one of us.
Maybe they were referring to someone else.
Someone's quacking. Jemus is only one. Oh no, what have we done?
What have we done?
I mean, one of you sound like it is coming from the bottom of a well. Okay, is it me? Everyone
Not on
talk.
my end.
I think
Hello?
you might sound a bit like you're echoing. Sure. But
Is
it's not bad, I'd say.
Okay, Meatball1, is it who just talked? Is it me? Or is it the third guy? The duck has a question. Okay. The next char guy is what Gordo Kagwe
heck?
says. You're the next char guy now.
I don't want to be the next car guy. Hey,
Yeah,
it's local. Is it
your
local?
mic looks. We'll say locally, your mic sounds just a slight bit more scuffed than Lens's. So
It's a cheap mic, but it's not a bad mic, and I'm not wearing headphones, so any
Yeah,
echo
yeah.
might come through while I'm
Tell it
talking.
from
But
bad
if I'm
mic.
silent, it should be fine.
Yeah, I don't even hear any talk through like us. So
Mhm.
you have a great setup. Local, forgot the name, sorry. It's okay. So is the C version done? Oh, I didn't answer. Thank you. Just curious because I'm interested in making a compiler. Great questions. If you don't know C++, don't fret. There's going to be solutions for C. Okay? So you're going to be able to write a front end in C because all it is eventually is we're going to have probably like a third-party front end type of thing where we just have a library that we call and it returns us IR that we know how to deal with. And then we just use the IR and boom, we used the third-party library. But that's going to be like a whole thing. That way you can change the front ends at runtime. But that's not needed. And that would basically mean that you can write it in any language that you'd like.
as long as it supports CFFI, which is most languages, yes.
Yeah.
I'd be worried about brainfuck, but other than that, you're probably fine.
That's right. Okay. Yeah, no problem, Zen Mystic. But yeah, we're not forgetting C. It's not like, but that version of the C compiler is done.
I'm
It's-
gonna write a simple C front end. You'll see
Yeah.
C again.
Because I said from any language, just wait. If someone's gonna make lcc.js.
I already joked about that.
Oh, you did. Okay.
I did. I'm already thinking about it. I'm not gonna do it, but I thought about it.
Yeah, you can. If someone wants to, they can use my. I have a CMake script that downloads the latest, that checks your Node.js version and downloads the appropriate headers, because the Node gyp thing never worked properly for me.
I could never
Just
get
use
that to work.
CMake.
What toolings are already implemented? Okay. That would be the language that this grammar describes, Intercept. By the way, we're going to have to either rename the grammar or move it.
Yeah, we can move the grammar later. I'll do that. Sure.
It's Intercept and lie. And basically there's plenty of examples for Intercept. For example, here's rule 110. Things are changing, but this is roughly how it will be. You can see that it's meant to be somewhat low level and imperative, but it's also meant to be inspired by functional languages. It's not a ton inspired by functional languages. We're not like, there's no monads yet. So the idea is we're gonna try and mix, just try and make a language that doesn't suck, I guess, is the main idea now. But
You still have the old version, because now all of that should say int, not integer. I didn't fix examples, only tests. I see what's happened.
yeah,
I see what happened.
and then we also have to
Are-
change my. Go ahead. What was that?
Are functions first class yet, or
Oh yeah,
are they still? Can you? Okay.
yeah. There's also lambdas.
Hmm.
So
Oh,
and
okay.
downwards funarg is a test that passes.
Yeah, that needs to be rewritten now, but yes.
Right.
I think at least it does it? Not even,
I
no.
think it's fine. Yeah.
Ooh.
But yeah, so you can pass a function as a parameter and call it, and then return that value from that function.
Yeah, what you will have to do now is because now you have to, the function body either has to be a block or with an equal sign, yes.
Yeah, kind of saw that coming.
We're gonna do that, we forgot about it, and now I did it. So
Fantastic. Yeah,
Where are
great.
semicolons required?
Nowhere.
Nowhere. Not
in
even the return statement that we just.
What was the question?
JavaScript vibes.
Sort of. It's just they're never required in any language, really. You can use them to disambiguate.
I mean, so where would you need them to like what situations would you need them to disambiguate besides the return statement that we just covered?
For example, a common one is if you say like 4 and then you have like some parentheses and you not do like 3 plus 5 or something. It thinks this is a function call sometimes.
That would be one.
So
Another one would be in languages where functions are just called by just putting them, juxtaposing them. So if you just have a, b, and that's a function call,
Right.
would be another situation where you would need that.
like if we could call display state like this.
Can you?
Not in this language, but some.
I mean, thinking about it, I don't think juxtaposition in this language does anything, does it?
Yeah, I think
do
we could.
that.
Yeah, we could totally do this.
More functional. You wanted it to be more like a functional language.
I
so
do
it could
like
do
that a lot. It's like Lisp, honestly, because this is like wrap that in parentheses.
Okay,
That's a
we could
Lisp
do it.
call.
We could do a thing. We could O4. I guess function type should probably still have the parentheses to not make us go insane passing them. But, or we might even be able to remove the parentheses in function types, I think. Because it's not like juxtaposition means anything there, does it? Oh, could just write this. Then if that looks too, we can remove the spaces around the colon if that's too.
If we go to the grammar, it's just like they're just kind of shoved in there.
Yeah, that's the in the type signature. That's parentheses around the type signatures we need. There you go.
Yeah. They're just shoved in there. I think we just do that.
Yeah.
Could just do that probably, yeah, because juxtaposition in this language doesn't mean anything simply because declarations don't use that syntax. So I don't think there's anything that uses just AB as a syntax.
This would be.
So
That's
definitely
actually
put that
really
in, yeah.
cool.
I
Yeah.
can definitely do that later, sure.
Fantastic.
So-
I would. Oh god.
That was horrible.
That was
Yeah, that sounds
horrible.
like it was an echo.
Someone's echoing.
So I
Wait, is
wanted
it
to
me?
interject
I think it's-
because we had those compile errors with nextcar. There is a definition for nextcar, but I may have done it wrong because I don't understand templates entirely.
Did you template it? Oh yeah, of course. If it's a template, the definition has to be in the header.
Well,
not in the C.
nextcar is not templated, but Lexer is on T
Yeah,
token.
yeah. That way, it's implicitly a template.
So does nextcar have to go in the header, even though it itself is not templated, but its type is?
Yes, if it's a member of a template, it has to. Yes.
Okay.
I'll take care
That
of
would be what
that.
I
Why is
thought.
Lexer?
If nextchar is always the same, there's a way to get around that by just calling there's a way to get around that. I'll take a look at that then.
So this isn't working.
I'm about to
this
commit
is
the
gonna
fix for
work
next.
because it has to see. You can tell this is the function itself is a template by the fact that it has a template argument list. So, what you're doing here, you're basically defining that for one specialization.
Yeah.
Not
I've
even that.
copied it over
Yeah,
there.
you're doing, no, yeah, this is the implementation. That's fine, but it's not going to work in the C. You have to put that in the header. Yeah.
It's not. The what?
So there's two ways of doing this. Either you put the entire thing in the header, which is what you typically do with templates, or you could just call a separate function that's defined out of line or something, of which there's only one instantiation.
I'm just going to move it to the header file.
Sure. As long as you don't end up with circular dependencies in the headers, that's fine.
Shouldn't do. It's just dealing with car. It might not like errors, but so just in case, I'll put it at the end. But I think that's fine. No, it's diag error, so it's fine. Okay. Okay.
But why is the Lexer templated on the token?
Because we're using it for all the front ends if you opt into it. It's a very generic, just, hey, we already implemented going to the next character in a source file for you. So if you don't want to rewrite the same boilerplate, just use our Lexer.
Yeah, because this handles new lines correctly and everything, so...
Cross-platform. This mess.
Yeah,
Alright,
it does
I'm
the
committing
Windows
that.
thing.
Hopefully it builds still. Hold on. Build.
But why is it generic over the token type? Oh, I see. Because Laie has different tokens
Yeah,
and
that's
Intercept has
exactly-
different tokens.
That's why, yeah.
Yeah.
Okay.
So if we want the Lexer to actually return to you a token properly, instead of just being a character by character thing, then we have to template it on the token.
We'll say,
We
does
do ha-
the Lexa base class use the token?
It doesn't, because it's not the way I'm used to parsing.
Okay, because if the Lexa base class doesn't need the token, we probably don't need to template it on that.
Yeah.
Could change that, probably.
The intercept Lexer does, but we could move
Yeah,
it out.
but it could just add the token itself. That's
Yeah.
the case.
If we still want
Some
the
complexity.
where else was the? No, I guess we don't need it. That's the only reason we needed it was for storage. So if we take it out, then yeah, we're gone.
I think you can just take it out then. We'll see. I'll look into that. I still need to do some like Lexa stuff, so
Yes.
Okay, so I've still got one error in the Lexer. Let me go fix that before I commit again.
Meatball1 asks, are you guys on the low-level language developers hangout Discord server? What a name.
It's a
No.
very long name.
They're mostly interested in compilers and stuff, language semantics, runtime, syntax, bike shedding. I started 5 days ago. I did HTML, CSS, which I am stopping now. Am learning JavaScript and C#.
like C#.
Best of luck on your journey. JavaScript will drive you insane. Good luck.
C# is definitely a better language than Java for beginners. I'd
Yeah.
say.
Yeah, C# isn't bad for your, like, if it's your first language, it's not the worst. Because you'll
And
learn
considering
a lot
the
of good
family of
things.
languages it's in, it's a good member of the family.
I'd agree. For what it is.
Uh-huh.
I'm just happy it's no longer just Microsoft.
I think also
Well, it's
someone
not.
mentioned. Let me just scroll up a bit. 3 plus 4 is 7. 7 minutes ago that you mentioned you were gonna wrap up the stream.
Yes, it's happening very soon.
Is it now?
Is it now? Well, you know, with time.
Also, why use auto? God,
That's what I said.
why is that unique point? Why do you? I think we were talking
Oh,
about when it
God.
returns, sure, but just use auto.
I was
All
just
of that.
I'm pretty sure you told me, you said the words, it returns a standard
Nobody
unique putter.
returns a unique pointer, but you can just use auto.
And then as I was writing module, you said, actually, it has to be LCC intercept module. And I was like, oh, yeah, you're right.
Yeah.
I'm
if
just
you wanted
saying.
to write it that way.
I'm just saying it. I was under duress.
You weren't gonna write auto to begin with, so anyway, just use auto.
I do have
Actually,
uncommitted
I don't know.
changes.
I
Or I
won't-
do have pushed
I-
changes.
prefer
I won't
this
change
way.
anything.
I don't know. I prefer this way because if you use auto, then you have no idea what the actual function returns. This might be confusing.
And you
But I don't
use
know.
the thing that tells you.
Argument generally for 2 reasons. 1, I can just mouse over it and the LSP tells me what it is.
Uh-huh.
2, you don't always care what it is. And also 3, this name is horribly long, so use auto pretty much always is what my
I
philosophy.
called mine file module so that you know what it is. Good naming makes good naming.
Okay.
Yeah, you definitely shouldn't
Okay.
be writing that entire type every time.
Probably not. I won't change anything because local has unstaged changes, and I'm just going to wait for
I
him.
mean, I didn't change
When I
that
see
line.
that, I'll just change it instinctively, don't worry.
Fantastic. But yeah, we
You know
got
what? I'll
this.
change it for you.
Sure.
Oh, it's still not even commented out. I'm not going to change it, actually. That's bad.
But yeah,
All right, what happens if I invoke the compiler on one of my files?
you should just print out what kind of the input files.
Well, no, I've tied it into the parser like you did.
Oh, geez. Yeah, good luck then.
I got it building. I fixed the Nextcar bug, and I fixed a couple other Lexer errors that came with it, and we're good now. So let me go
Oh.
make an example file.
Zen Mystic says, I was going to do my own language and stream it, but now I guess I don't have to. Don't want to be accused of coping. The copium was real with this one. What'd you say? It is just coping, right? I swear I heard somebody talk. It's probably just a voice in my head. I'm hallucinating.
I
You're-
mean, like 2 people were talking, but if we don't tell him, he'll think he's crazy, right?
Sure.
Your
I was
version
crazy.
seems to have a lot in what I thought of before I found this place. Well, I guess if it's okay. I had originally did a search bar for if there were any tutorials and this came up. Copying, lol. Oh,
Okay, not coping.
that makes more
Coping.
sense. I was like, why would you? Coping is fine. Copying. Yeah, don't worry about copying. You can make an Intercept 2.0. It's under the MIT license. I mean, I don't wish that you would, but if you wish to, no one can legally stop you. Yeah, do it. So many
Call
people
it
do
intercept.
this. That's right. I would agree. I think you should stream, and if you're a good streamer, I'll help you out. We'll all be a little community and host each other. And if you want, make a front end for LCC. Yes, that's what I recommend. If you have a language in mind, just make a front end for LCC. I mean, it's
If you
not
want to
done.
learn the whole process, that won't get you the whole process, but it'll get you the first half.
Exactly. Then what you can do is you can take your parser because it's under MIT. It's totally yours if you want it. And then basically you just take the parser under MIT. You can use it in your project and write your own backend if that's your thing. If you're like
Or use
like
all
me.
VM, that's always an option.
Yeah,
Mhm.
I will never recommend that, but you can do that. But yeah, thank you everybody so much for watching. This has been awesome. And does anybody here have anything to shout out? These fantastic people.
Just the stream I'm trying to start doing.
Okay, check out the description. Subscribe to Local. He has a YouTube channel and
Yes,
he streams
I
there.
do I do technically have a Patreon, but I mostly put the Conlangi stuff for Agma now on there probably, so...
Eternal has a Patreon. That'll be in the description. Check out the description to support these lovely people.
Dang, I gotta make a Patreon now.
Because I need to start uploading more stuff on there, though.
Join the Discord to get announcements every time I go live, as well as, just be a part of this lovely community. Talk about philosophy, do all these things. Anyway, I gotta go. So, I gotta run. I'm running fast. Bye-bye, everybody. Thank you so much, Zorchenheimer. You're still here. You're a legend. Thanks for rating. Oh, I almost hit the disconnect instead of stop streaming. I'm a genius.